Hi there. Welcome to this video series on Amazon Web Services. Throughout this course, you will learn how to use and when to implement many of the tools offered by Amazon Web Services. We will cover topics like distributed computing, multi-tier architectures, virtual machines, storage, databases, and much more. We will see just how simple and cost-effective it is to achieve a superior level of high availability, fault tolerance, and security in our infrastructure and our applications. We will review a number of use cases designed to spark your imagination and exemplify architecting solutions within the rich and varied ecosystem that is Amazon Web Services. Just a little about myself and my background. I have been developing web and mobile applications for the past 15 years and started using Amazon Web Services in early 2009. In the last 7 years, Amazon Web Services has matured incredibly, and I have continually strived to deepen my knowledge and experience with their offerings by working with startups to build cloud-native applications, as well as helping established companies migrate to AWS. As of this video, I have 4 out of 5 certifications, including the Solutions Architect Professional, and have delivered official AWS training to Fortune 500 companies around the world. Before we get into the technical details of various Amazon Web Services, let's first look at the big picture. In this lesson, we will look at AWS Global Infrastructure and review some very foundational terms and concepts that will apply to everything we will cover from here on. In this lesson, we will explore AWS data centers and their locations around the world, as well as a high-level overview of the kinds of services offered. All right, so first of all, what is cloud computing? So a number of years ago, the National Institute of Standards and Technology, which is a government organization dedicated to maintaining standards of different things, got together with industry leaders and said, you know what, cloud computing, this term is a marketing term, but what does it mean? Let's all be on the same page in terms of what we mean by cloud computing. So it comes down to these 5 characteristics. The first one being on demand. On demand means that you get what you need when you need it. If you need a virtual machine now, if you need storage now, you can go and get it now. And maybe it takes a few minutes to become available, but you get it right away. You don't have to call someone and describe what you need and then wait several weeks for it to be available. You get what you need when you need it. Broad network access means that you have access to private networking, public networking, access to the internet, and a range of network tools. Resource pooling means that even though you might get a virtual machine that's dedicated to you, you may get storage or even a physical server dedicated to you. A lot of the other resources that we're dealing with, such as network, power, cooling, the rack, the building, are shared across a number of different clients, a number of tenants. So that's where we get this concept of resource pooling. Cloud computing is not talking about one company building their own data center for themselves. We're talking about people coming together to leverage a large group of computers and resources. Rapid elasticity is the concept where, say we need to scale our web fleet out in order to meet demand, or we want to scale it in order to save money. We want to scale our storage capacity. We want to scale our database capacity. The ability to do that very quickly on demand is rapid elasticity. Growing when we need to grow is rapid elasticity. And it's a very, very key point about cloud computing that we will be exploring throughout this course. And then, of course, the last point, measured service. The other way to say that is pay as you go, or pay for what you use. Meaning that if I run a machine for an hour, then I pay for an hour. If I run it for a month, I pay for a month. Typically with cloud computing, there's no mandatory long-term contracts. And then, of course, cloud computing comes in typically 3 different models. Now, what we're going to be exploring in this course is the infrastructure as a service model. Amazon Web Services follows that. But there are also the software as a service and platform as a service models as well. All right, so let's take a look at the regions that are available within Amazon Web Services. Amazon Web Services has more than a dozen regions. At the time of this video, we have 14 available regions with more on the way. So starting here on the west coast of the United States, we have Oregon, California, GovCloud, which is for government entities. We have a new region recently launched in Ohio, Virginia. Going down to South America, we have Sao Paulo, Brazil. Starting in Europe, we have Ireland, Germany. Going into Asia Pacific, we have Mumbai in India, Singapore, Sydney, Australia, Beijing, China, Seoul, Korea, and of course, Tokyo. Now, regions are the primary building block of Amazon Web Services. When you go to launch resources such as virtual machines, storage, load balancers, databases, so on and so forth, you generally will pick a region. And as we're going to talk about, some things don't require a region, but most of what you do will require that you choose a region where that particular resource is located. Regions are that primary center, and typically we choose regions based on perhaps latency to your end users. You might choose a region based on cost. Perhaps you aren't necessarily serving end users from that region, but you just want a region that is cheaper than others. So it's important to note that some services are more expensive in certain regions. So cost in Amazon Web Services is determined by the region. It's not always the same. Another reason you might choose one region over the other is for security compliance. Certain countries, certain regions like the EU have laws around personally identifiable information that are different than other countries, and they govern how data can move and where it can go. So you might choose a region based on that. For large sites, such as Netflix and sites like that, sites that are serving a global audience, you may very well choose multiple regions. And this is a very common practice. You might choose multiple regions simply for disaster recovery. You might choose multiple regions so that you can serve different audiences, a US audience versus a European or South American audience. So again, these are our regions, 14 active regions as of the time of this video. All right, so let's talk about availability zones. Amazon Web Services is rather tight-lipped about how they build things, for good reason, for security. So we do know that availability zones are a collection of data centers. And we do know that when they build availability zones, they consider a number of things such as floodplains, fault lines. They put each availability zone on a separate power grid. They're connected with private fiber. So here, our example is the Oregon region, otherwise known as US West 2. So you can see here in this particular region, we have 3 availability zones, US West 2A, 2B, and 2C. And this is the typical pattern that we will see as we continue to work with Amazon Web Services throughout this course. Every region has at least 2 availability zones. Some, such as Oregon and Ohio, have 3. Others, like US East, might even have more, but they all have at least 2. So while regions might be the primary building block, availability zones are really the key to high availability and fault tolerance. As we will explore, when we start to build our infrastructures and deploy our applications into Amazon Web Services, we want to leverage as many availability zones as possible. What we want is a system that is not only resilient to the loss of a machine, but we want a system that's resilient to the loss of a data center. We're asking a fundamental question: what happens when a data center fails? What happens when a data center becomes unreachable? So a good answer to that question is, well, we have multiple data centers. We have our application is running in more than one data center. So if we were using the Oregon region, we would leverage all 3 availability zones, A, B, and C. We would spread our application across multiple machines. We would spread our databases, our storage, our content across all the availability zones so that we have high availability, fault tolerance, and durability. So again, availability zones are a collection of data centers connected with private fiber and are the key to high availability and fault tolerance within Amazon Web Services. So edge locations in Amazon Web Services do two things. They serve for two different services, one being Amazon CloudFront, which is Amazon Web Services content delivery network. When you want to deliver content to your end users, you can get the best performance by delivering that content from a server that is closest to them, a server that has the lowest latency. If you're a US business serving an audience in Europe, why make your customers cross the Atlantic and the continental United States just to get that content? It would be better for them to get that content from a server here in Europe. Likewise, if you have an audience in Asia, they should download your content from a server in Asia. So an edge location can help do that. An edge location, as used with Amazon CloudFront, will cache that content so that in the example where you have, let's say, someone in Texas goes to download an image, they may be routed to somewhere over here on the East Coast, and that particular edge location will cache that content so that it can be delivered more quickly to your end user the next time it's requested. The other service that edge locations serve for is Amazon Route 53, which is Amazon Web Services global DNS service. So when a user does a DNS query, they can get that IP address back or the answer of that query as quickly as possible. At the time of this video, there are over 50 edge locations all over the world, and you will see here, compared to the regions that we've talked about, the edge locations are not necessarily in a region. Some of them are, but most of the edge locations are actually not within a region, but they stand on their own. Now, it's a common question as to what kind of control we have over edge locations. We have some control over when we use these services like CloudFront. We do have some control over what edge locations are used, such as US versus Europe versus Asia Pacific, but we don't have any direct access to the edge location itself. We don't necessarily have any control over the content that an edge location has. We can't pick and choose what content goes to what edge location. We generally just choose whether we want to use US, Europe, and/or Asia Pacific. So again, edge locations serve Amazon Web Services content delivery network, known as Amazon CloudFront. They also serve the DNS service known as Amazon Route 53. Okay, so let's talk about the scope of services within Amazon Web Services. As you start to use Amazon Web Services, as we start to launch virtual machines, storage, databases, and so on, we'll start to see that certain services have a particular scope. Some services are considered to be global, such as AWS IAM, or the Identity and Access Management, Amazon CloudFront, Amazon Route 53. These services are global because we don't need to choose a particular region or availability zone when we use them. In the case of AWS IAM, or Identity and Access Management, if we create users and groups and start to give those users and groups permissions, making a change in that service takes effect everywhere. It's not dependent on any particular region, so that's what makes it global. A regional service, such as Amazon DynamoDB or Amazon Simple Storage Service, means that when we go to launch that particular resource, let's say that we go to create an Amazon DynamoDB table or an Amazon Simple Storage Service bucket, we will choose the region, and that particular service, using Amazon DynamoDB as an example, that particular service is inherently highly available and fault tolerant and durable. It uses all of the availability zones within that region already under the hood. So we don't have to worry about the availability zone. That's already done for us. We just choose what region we want that Amazon DynamoDB table to be in. Other services like the Amazon Elastic Compute Cloud. When we get into networking and we start choosing subnets, or we want to create a volume for our virtual machine with Amazon Elastic Block Store, those kinds of services are specific to an availability zone. Meaning that, as an example, if we launch a virtual machine within Amazon Elastic Compute Cloud, we will choose an availability zone. And if we want to attach an Amazon Elastic Block Store volume to that machine, both of them have to be in the same availability zone. So that's where we get that particular scope of services. So again, services can be either global, meaning that we don't choose a region at all. They could be regional, meaning that we don't choose an availability zone, but we just choose the region. Or they could be specific to an availability zone, such as is the case with Amazon Elastic Compute Cloud. So now let's take a look at a service overview of Amazon Web Services. We'll look at the console and just an overall view of the services that are offered. You can see here that I've logged into the Amazon Web Services console. In the top right corner, I can choose what region I want to operate from. In this particular case, I'm operating out of Virginia. Some services like billing and certain things will always be out of this particular region. But for now, it doesn't really matter. I'm just going to go through an overview of what Amazon Web Services has to offer. But if we wanted to change into a different region, we would just choose it from here. And now you can see that we've changed to a different region. So you can see that Amazon Web Services has a very rich set of services and tools that they offer. You can see that here on the initial dashboard that they are broken down into various categories like compute, where we find things like Amazon Elastic Compute Cloud, or EC2. We also have other things that we'll talk about later, such as Amazon Elastic Beanstalk and Lambda. We also have storage, like Amazon Simple Storage Service and Amazon CloudFront. We have databases, such as the Amazon Relational Database Service and Amazon DynamoDB, that we'll talk about in more detail later on. We have networking, analytics, security. This is where we're going to talk about identity and access management. We're going to talk about various management tools like Amazon CloudWatch, how to monitor, how to automate our infrastructures. We have developer tools, DevOps tools, just different ways of deploying our applications into Amazon. And then, of course, the Internet of Things is a hot topic these days. Amazon is pushing really heavily to make that world a whole lot easier, to make it easier to connect all of these devices and gather all of this data with the Internet of Things. Game development, mobile services that we're going to talk about, a number of application services, core building blocks of various pieces of software. So you can see, again, Amazon Web Services is a very rich and varied environment. And you will see that there's a lot here. It's just not possible for one course to cover everything. Some of these services are even just one service could be rich enough for its own course. So you will notice that throughout this particular course, we won't cover everything. But I've done my best to pull out the things that are the most important. One of the most important facets of a reliable environment is its security. And security in AWS starts with our accounts, users, groups, and access credentials. In this lesson, we will cover authentication and authorization methods in AWS, as well as best practices. All right, so let's talk about the AWS Identity and Access Management Service. Within AWS, we need a way to authenticate and authorize our users. Authentication being knowing who that person is, authorization being what they're allowed to do. Now, of course, just like any system, we have the ability to create users and groups of users. We have the ability to control our password policy, and it's recommended that we set a strong password policy, including disallowing the last certain number of passwords. Perhaps the last 2 or 3 or 4 passwords should not be reused. We also have the ability to enable multi-factor authentication. So just in case we might not be familiar with that, multi-factor authentication could be described as something you have, something you know, and something you are. Now, the something you are would be biometrics like fingerprints, iris scan, and of course those aren't available here within the AWS Identity and Access Management Service, but the other two are. Something you know would be like your username and your password. Something you have would be a multi-factor authentication or an MFA device, such as a key fob or a virtual MFA device on your cell phone. So MFA or multi-factor authentication is fulfilling at least 2 of those. So something you know, the username and password, combined with something you have would fulfill the multi-factor authentication. It just adds that extra layer of security to your account, and it's highly recommended and considered best practice that we enable that and use that for all members who especially need to log into the console, or in other cases that we'll talk about later when you're doing special types of things like accessing your production account. Now, it's really important to note that what we're talking about here, creating users and groups, authenticating and authorizing, this is meant for authenticating and authorizing against the Amazon Web Services API. When you think about realms of authentication, like the areas into which we need to authenticate our users, that would be one being the AWS API, which is what the Identity and Access Management Service is for. And then, of course, we have our operating system. If we install applications on that operating system or databases, then they would have their own realm of authentication and their own set of users. So it's important to know that what we're talking about here within the IAM service, the Identity and Access Management, that this is specifically for authenticating against the AWS API. It is not to be used for OS level authentication or application or database level authentication, except in the case of Amazon DynamoDB, and we'll talk about that later. So again, the AWS Identity and Access Management Service is for authenticating and authorizing users and groups of users against the Amazon Web Services API. All right, so now let's take a look at a demo of creating a user and group within AWS Identity and Access Management. You can see that I'm already logged into the AWS console, and from here I'm going to go to the Identity and Access Management Service. Here's the dashboard of Identity and Access Management. You can see at a glance that I already have a couple of users. I have one group already, an admin group. I have some roles. You can also see that the IAM service gives us a checklist of things that we need to do to ensure that we have the greatest security within our environment. So from here, first thing I want to do is create a user for Jane Doe. So I'm going to go ahead and go to my users. I'm going to create a new user, and here I'm going to say jane.doe. We're going to talk about access keys later, but for now I'm going to uncheck that and create. And you can see now I have the Jane Doe user. Now at this point, you can see here that my user has a password, but Jane does not. So at this point, Jane can't do anything. She doesn't have access to the console. She doesn't have access keys for the CLI. Again, we'll talk about access keys here later on. But Jane has no permissions either. She just has an account that she can't access and can't do anything with. In order for Jane to be able to actually do something, she needs to at least be able to log into the console. And in order to log in, you need a password. So I'm going to click through to the details of Jane's user, make sure that I'm on the Security Credentials tab. I'm going to come down here to Manage Password, and from here, I'm going to just assign an auto-generated password, and I want to ensure that Jane is required to change that next time she logs in. So once I hit Apply, this is the only time that I will be able to see that password that was generated. So from here, I would copy and paste this and give it to Jane in some kind of secure way. over an encrypted connection of some kind. And that's the only time I would ever share credentials, is when I know that this user is going to be prompted to change their password when they log in. So I'm going to go ahead and close that. And you can see here that Jane does have a password. So now she has access to the console, but she still doesn't have any permissions. I'm going to grant her permissions by way of using a group. And so I'm going to come over here to the groups. You can see I already have an admin group that my user is a part of, but I want to create a group for developers. So I'm going to create a group. This is totally arbitrary what you name it. There's nothing in Amazon Web Services that says you have to name it in any particular way. I'm going to call this one developers because that's what Jane is in this example. And from here, now the wizard is prompting us to attach policies. And we're going to talk about policies later. But for now, suffice it to say that policies are a way of granting our user permissions to do things. And so I want our developers to be able to launch EC2 instances or virtual machines. So I'm going to give them EC2 full access. And I'm going to go ahead and create that group. And now you can see that we have a developers group, but we don't have any users in it yet. So I'm going to click through. I'm going to add users to the group, select Jane, click add users, and now you can see that Jane is a member of the developers group. We can see that the developers group has access to Amazon EC2. Okay, so now that we've created our users and groups, let's take a look at creating access keys for that user. So again, we've created our Jane Doe user. We've given her a password so that she can log into the console, but perhaps Jane wants to use the Amazon command line tools, or she wants to use the SDK to develop locally. In those cases, she needs access keys as a way to authenticate against the AWS API. So the password is to log into the console, but in order to use the CLI or the SDK, she needs access keys. And again, as we've talked about, this kind of authentication and authorization is specifically for the AWS API. It is not for operating system or application level authentication. So here I'm on the details of the Jane Doe user. So I'm going to make sure that I'm on the Security Credentials tab, and you can see that she does not have any access keys yet. So I'm going to create the access key. Now at this point, this is the only time that I will be able to see these access keys. If I don't copy and paste them from here, I will never be able to see them again. I would have to delete them and recreate them. So I want to be sure to copy and paste these. I'm going to copy these. Now generally, if I'm doing this for a user, I want to be sure to transmit these in a secure way over some kind of encrypted connection. I could copy and paste. I could also download these as a text file and then transmit that text file to Jane, again, in some kind of secure way. So I'm going to go ahead and copy those, close that, and you can see now that Jane has an access key. Now I can see the key, but I can't see the secret. There's two parts to it. There's a public part and then what we might consider a private part, the secret part that I can't see. Now, the best approach might be to enable our users to create their own access keys so that they don't have to be transmitted between, an admin and the user. They can just get them directly, and that ensures that the keys are kept much more secure. So again, that's how we create access keys for our users. This will be implemented within the local Amazon command line tools or the SDK for local development. So here let's discuss permissions and policies within the AWS Identity and Access Management Service. So we've talked about how we allow our users to authenticate and authorize against the AWS API. It's one thing to have a user account, but that user account by default does not allow your user to do anything. In order for our users to be able to actually do their job and create resources within Amazon Web Services, we need to grant them permissions. We have to have an explicit allow somewhere within their account in order for them to be able to do anything. And we do that by way of policies. Policies are just a simple JSON text, JSON being JavaScript object notation that we'll talk about later on. Now we have two different types of policies. We have what we call managed policies, which are top-level, first-class objects that can be directly created and managed apart from other resources. And you can see that we have both an AWS managed, meaning that these are policies that are created and managed by Amazon Web Services. And then we have customer managed policies. These are policies that we create and manage on our own. And so it's common for customers to have their own library of policies to apply to different types of users or different groups of users. And then, of course, we can have the other type of policy would be what we call an inline policy. The inline policy would be where you would put that policy directly onto a user's account rather than referencing a managed policy. Now, we have a couple of ways that we can create policies. We can either use a generator, which is a simple UI tool that Amazon Web Services gives us that allows us to choose the service, the type of actions, and it will write the JSON policy for us. We could also just handwrite it if we want to as well, or copy and paste. Now, it's important to understand the evaluation logic of policies. They all start with a default implicit deny. So again, you can't do anything unless you have an explicit allow. So the policy evaluation logic first starts with that implicit deny. Then it actually looks for an explicit deny. That's important because generally you use the explicit denies, and we'll talk about this more later on, but you would use an explicit deny to create perhaps what you could call some safety rails around things. So with an explicit deny, it can never be overridden. If you say that a user is not allowed to do something, then no matter where else they might be allowed, the explicit deny will always win. That's the great security layer that we have access to within policies. And then, of course, if it doesn't find an explicit deny, it will then look for an explicit allow. So remember that they start with an implicit deny, and they look for that explicit deny, which overrides everything. And then in order for a user to be able to do anything, they have to have somewhere an explicit allow. So before we look at an example policy, I want to talk about one other thing that's really important to understand. This is very, very key thing in order to understand security in Amazon, in order to understand writing policies. And it's called the Amazon resource name. An Amazon resource name is a way of uniquely identifying a particular resource across all of Amazon. When you imagine that Amazon Web Services has over 1 million paying customers across 14 regions, 38 availability zones, across the entire globe, there are lots and lots and lots of resources. And some customers, just one customer, may be running thousands of virtual machines. They may have dozens of databases. So one customer might have millions and millions, perhaps even billions of objects stored within Amazon's simple storage service. It's important to be able to uniquely identify every single resource within all of Amazon Web Services, and we can do that with an Amazon resource name. So you'll notice here that the Amazon resource name follows a particular pattern. They all start with ARN:. These different parts of the ARN are separated by colons. So you can see that it will be ARN partition, the partition being the high-level organization of Amazon Web Services. Most of the partitions will be named AWS. If you're operating out of the China region, one other example is the partition in that particular case might be AWS-CN. But for the most part, they will all be AWS. And then, of course, comes the name of the service, the region that we're operating in, such as US West 2 or US East 1, the account ID, the resource type, what kind of resource we're dealing with, whether it's an S3 bucket, an EC2 virtual machine, or so on, and then of course the actual name of the resource. Some resources are separated by a slash, sometimes it's a colon. It's always best to just go back to the documentation. I've been using Amazon Web Services for 7 years now, and I constantly go back to the documentation. These details are too much to remember, so make the documentation your best friend in these cases. So just a couple of examples of ARNs. If we wanted to uniquely identify one user out of the millions of users that exist within Amazon Web Services, this might be our ARN. You'll see here that it follows that pattern. ARN, AWS, the name of the service, IAM being the service here, and you'll notice that the region is left blank. You'll see here that for global services like IAM, the region is not necessary because it doesn't matter what region. And then of course we have the account ID, and as we'll talk about later, it's very possible and it's very common, and in fact it's suggested, recommended best practice to leverage multiple accounts for your environment, and we'll talk more about that later. But here we have the account ID. And then of course what we're saying, the resource type in this case is a user, not a group, not a role, not anything else but a user, and then of course the name of that user, in this example being B. Smith. Another example of an ARN is in the case of, here the example is for Amazon Simple Storage Service, otherwise known as S3. It's ARN, AWS, S3, and you can see here in this example that the region and the account number are both left blank, and that's because the name of the bucket is itself globally unique, and because of that we don't need the region or the account ID. In the last example, all of them are filled in, the name of the service, the region, the account ID. In this particular case, we are talking about the Amazon Relational Database Service, and we are targeting a very specific database within a particular account, within a particular region. So again, these are the Amazon resource names, and a very important thing to understand when we get into writing policies. So let's take a look at this example policy. Now again, as we've talked about, policies are written in JSON, JavaScript Object Notation. It's just a simple collection of key value pairs. Here, one of the first things that we need within our policy is the version, and we have our key over here called version. It's quoted, and then the value separated by a colon, also quoted. Now the version in this case is not a semantic version like 1.1 or 2.4. It's the date at which this policy was last published, and we can find those versions within the AWS documentation. The next thing that we need in our policy is a collection of statements, and you can see that the square bracket denotes a list or an array. In this case we only have one, but it's still a collection. Now here what we're saying is that we're allowing this user to perform these two actions. We can see that actions are prefixed by the name of the service. In this case, Amazon Simple Storage Service, or S3, is prefixed here to these two actions. So it's like a namespace for those particular actions. And we're saying that we're going to allow this user or group of users to download and upload to this particular resource. And in this example, as we've talked about this resource using an ARN, we're specifying that they're allowed to perform these actions anywhere within the bucket. So you'll notice that the bucket would be my bucket, but the /* is yet another thing. The / indicates everything within the bucket. So again, the bucket is one resource, objects within the bucket are another, and we'll talk more about how the Simple Storage Service works later on. So as we've talked about, the evaluation logic, it starts with the implicit deny. It will first look for an explicit deny and then look for an explicit allow. So it's also important to note that users or group of users can have multiple policies, and each policy can have multiple statements. So it would be possible that a user or group of users somewhere within their policies has a deny that would override this allow. It doesn't matter in what order. The evaluation logic would first look for a deny, and then only if it didn't find one would this allow actually take effect. So again, this is an example, just one example of a policy within AWS Identity and Access Management Service. So ultimately what we can see based on that last example, that policies are essentially just collections of statements. It is possible for a user or group of users to have multiple policies attached. The statements simply specify, in the case of resource-based policies, as we'll talk about more later on, we specify the who. Otherwise, the who is already implicit depending on who the policy is attached to. We specify actions, the things that that user is allowed to do. We specify resources, the actual Amazon Web Services resources that our users are allowed to do things with. And then, of course, we also have the ability to specify conditions. Just a few examples of the possibilities would be perhaps we want to limit the time of day. Perhaps we want to say these users are allowed to do certain things only during working hours. Perhaps we want to limit them from a specific IP address, such as our corporate static IP. Perhaps we want to say that a group of users is only allowed to do something if that resource, such as a virtual machine or a database, is tagged in a particular way. So with permissions via policies, we have very, very fine-grained control over who can do what to what resources throughout our Amazon Web Services environment. So now let's take a look at an example of how we would go about creating and attaching policies. So you can see I'm already logged into the console. I'm on the Identity and Access Management dashboard. And from here, I'm going to go over to policies. You can see, as we've talked about, policies can be, managed policies can be first-class objects. And we can, of course, filter by either Amazon managed policies or customer managed policies. So I'm going to go ahead and filter by customer managed, and you can see that I've got a few policies that I've created over the years for doing personal things. But I want to go ahead, for the sake of this demo, create one. So I'm going to create a policy, and from here, I have a number of options. I could either copy one from an Amazon policy and then edit it to my liking. I could use the policy generator, or I could, using this last option, I could just copy and paste and write it out in JSON. I typically don't like to do that just because there's a lot of room for error in the JSON document. It has to be valid. So I generally like to use the generator. That way I know that it's going to create the appropriate syntax. So for here, I'm going to select the policy generator. And for this policy, I want to allow, and I'm going to say that I want my developers, let's say we want to attach this to our developers. I'm going to allow them EC2, and I'm going to say that I have the option to say all actions, but here maybe I only want them to be able to launch certain EC2 instances, create virtual machines. You can see here there are a lot of things that we could give them access to within EC2, but I don't want them to have access to all of it. I want them to have access to maybe tagging resources. I want them to be able to create disk volumes, as we'll talk about later. I want them to be able to, let me scroll all the way to the bottom here. I want them to be able to launch virtual machines, which is this particular action, run instances. I don't want them to be able to terminate instances, though. That's a dangerous operation. I want to keep this particular group of people from being able to do that, so I'm going to make sure that I leave that one unchecked. So again, this is least privilege. I'm giving them just enough to do their job. And here, the ARN, because I'm choosing specific service and actions, I can just say star. In this particular case, I can just say, you know what, you can do these on across everything, across all resources, And of course, because they are prefixed with EC2, they would only apply to EC2 resources anyway. So now when I click the next step, you can see here that I have the policy that's been created. I have a series, only one statement that says they're allowed to do these 3 actions on any resource. I'm going to go ahead and name this something else. I'm going to call this EC2 access for developers. And again, that's arbitrary. That's up to you. Whatever you want to name it, whatever makes sense for your particular business. I'm going to create the policy. And of course, I can filter it. If I want to go back and find it, I can say filter by customer managed policies. And here we go. Here is that particular policy. And you can see we could edit that if we wanted to. We could see that it's not attached to anything. So let's go back to the group that we created earlier. Earlier, we created a group and we gave that group EC2 full access and an AWS managed policy. But that particular policy grants far too many permissions. I don't want our developers ultimately to have that many permissions. I want to, again, grant least privilege. So I'm going to detach that policy and I want to attach the policy that we just created. So I'm going to filter by customer managed policy. I'm going to find, here's my EC2 access for developers that I want. I'm going to click that and attach. And now, if I hit show policy, you can see that my developers group is allowed to create tags on EC2 resources, create volumes, and launch EC2 instances. And that's that for creating and attaching policies. So now let's take a look at another really important and powerful feature within AWS called roles. Roles can be thought of as an alternate form of authentication. They provide us with what we call temporary credentials. Now let's first start with what not to do. When we have a credential such as a username and password, we have access keys that we'll talk about later on. What we don't want to do is embed those within our code, because if they're in our code and we go and publish our code to a repo, it's possible for other people to find them. It's possible for other people to use them in ways that they weren't intended. So we don't want to embed our keys in the code. Even from a logistical standpoint, a good practice is to rotate our credentials regularly, changing passwords, changing access keys, and by doing that, it means that we have to go and update code. If we embed them within the code or in environment variables, now it adds an extra step that we have to take care of. So we don't want to do that. We also don't want to share credentials with other people. And I've seen customers do this, and it causes a lot of problems downstream. If you're having multiple people use one set of credentials and then they change a password or whatever, it just causes a lot of downstream effects. So what we want is a way to authenticate and authorize a user, but without having to give them or without having to embed or share some long-term credentials. So the answer to that is using roles. Roles can be used in a number of different ways. We can attach a role to an EC2 instance or a virtual machine and have that machine authenticate via that role. That way we don't have to embed credentials. We can have other AWS services leverage roles on our behalf. We could have a user assume a role so that their normal day-to-day is done with their account, but if they want to do something special or switch over into another account, then perhaps they would use a role to do that. You can also use roles to authenticate for third-party accounts as well. So let's take a look at an EC2 role example. In this example, let's start with an EC2 instance or a virtual machine. Now, again, we don't want to embed credentials, any kind of long-term credentials in this machine. We don't want to embed it into environment variables. We don't want it in our code. So what we're going to do at the time we create this machine, we're going to attach a role to it. And we're going to give the role the permissions that this machine needs to access, such as in this particular example, perhaps this EC2 instance needs to communicate, upload, and or download files and objects to the Amazon Simple Storage Service. So the way that the role works is that using either the AWS CLI tools or leveraging the SDK, if our application is leveraging the SDK, then either one of these will automatically detect that this machine has this role attached. It will then, behind the scenes, completely automated, done for us. We don't have to worry about how all this works. It's just done for us. The CLI or the SDK will go to the AWS Security Token Service and request temporary credentials based on that role. The AWS Security Token Service will deliver those temporary credentials. The CLI and or the SDK will then apply those credentials and then use them in order to authenticate against whatever service that we're trying to reach, in this example, Amazon S3. The CLI and the SDK will also automatically renew those credentials when they expire. So again, temporary credentials, in this case using a role, these credentials generally live for about 15 minutes. In other cases, we can control that and push that time out to a longer period, but in most cases, they will default to 15 minutes. And then, of course, these tools will cache those credentials, and once they expire, they will automatically renew them for us. And so leveraging roles in this way is a really powerful and really flexible feature that enables a very high degree of security without us having to embed keys and credentials into our code or environment variables. Okay, so now let's take a look at a demo of creating roles. You can see here I'm logged into the Amazon console. I'm in the IAM service, and I've clicked over here into the roles section. You can see that I don't have any roles yet. Now again, roles come in a number of different flavors. They can be used to attach to an EC2 virtual machine. They can be used by other AWS services. They can be used for cross-account access. So picking up where we talked about the last example, the last use case of using a role for an EC2 instance, I'm going to create a new role, and perhaps I have an application, my web application, or some kind of an API running on an EC2 virtual machine, and that particular application needs access to S3, Amazon Simple Storage Service. So I'm going to call this one my application. And again, you can see that we have all these different types of service roles, roles for various types of AWS services. We have roles for cross-account access and roles for identity providers, or a way to use federated users for your organization. In this example, we want to use a service role, and I want to use the very first one, the EC2, and it says that it allows EC2 instances to call AWS services on your behalf. Again, this is a way that we can get our EC2 instances access to various other Amazon resources without having to embed credentials such as access keys into our environment variables or into our code. That's exactly what we don't want to do. So here I want to filter by S3, and just as an example, I'm going to choose S3 full access. This is not necessarily how we might do it in production, but just for the sake of this demo, I want to give this particular application access to S3. And in fact, let's do S3 read-only access. That way, our application is perhaps pulling information out of S3 rather than writing. So I'm going to choose that policy and click Next. Now we have created a role. We've attached a policy to that role. I'm going to go ahead and finalize that. And you can see now that we have our role. And you can see that our role is allowed to read from S3. And we can see that the trust relationship says that this role is trusting the EC2 service. Now, when we go to launch EC2 instances or virtual machines, we can apply this role at the time we launch that machine, and then any application, and that's important to know, any application running on that virtual machine will be able to read from S3. If you log in to the operating system of that machine and use the CLI tools, you can get access to S3. If your application that is deployed to that machine uses the SDK, it can get access to S3. So that is creating roles for use in EC2. All right, so let's take a look at federated users within AWS. In small organizations, when you have 2 or 3, maybe even a dozen users within your organization, people that are actually using AWS, creating and managing resources, then it's really easy to just go in and create users directly within the AWS Identity and Access Management Service. But in larger organizations where you have potentially dozens or hundreds or thousands of employees all needing access to AWS, it becomes really difficult and challenging to manage those accounts both on the corporate side in your own directory and in a separate directory within AWS. And that's exactly what we don't want to do. In those particular situations, we want to leverage federated users. In large organizations where you have your existing directory, perhaps you're using LDAP or Active Directory, you already have a directory of users. You already know who they are. You can also determine what they're allowed to do by using roles, as we've talked about. So federated users means that you are taking someone who you already know and giving them temporary access into AWS based on temporary credentials. So by doing this, we could create a single sign-on service where they sign into one place, such as your corporate network, and then through that initial sign-on, they then have access into AWS. We also have the ability to federate web and mobile application users. So in the cases where we have a mobile application and that mobile application needs access to Amazon services such as Amazon S3 or Amazon DynamoDB, then it's possible to federate millions of mobile application users and through that give them temporary credentials, allow them to directly upload and download to Amazon S3, and by doing that we could potentially even completely bypass back-end APIs and proxies and allow those mobile applications to go directly to AWS services. So let's take a look at a federated users example. Here, what we're talking about is authenticating our corporate users against an existing directory. In this case, it could be, again, LDAP, it could be Active Directory, it could just be a database, a custom application looking to a database. So our users authenticate to our on-premises identity broker. That could be some custom application, an intranet, whatever it is. We're looking for their credentials, and then we're going to authenticate them against our directory. Now we know who they are, and part of that directory here says that this particular user, at the time that they log on, needs access to AWS. And so once it sees that, our identity broker will then come over to make a call to the AWS Security Token Service and pass in certain information such as the name of a role that we want that user to assume, or we could also just pass in SAML. We could pass in a policy directly, and then the Security Token Service will return, again, temporary credentials. We can control the lifespan of those credentials. They default to 15 minutes, but we could push that out up to 36 hours. Once we return those credentials, we could do one of two things. We could either just display those credentials here to the user so that they could use them in their command line as environment variables. They could place them into the SDK for local development. Or if they're just doing things within the AWS console, we could just simply redirect their browser to the AWS console and have them already signed in and start work right away. So again, this is an example of federated users leveraging an existing directory. This is really powerful and useful when you have existing users, dozens, hundreds, thousands of existing users who need access into AWS, and you don't want to recreate their accounts in a separate location. Okay, so now let's run through another demo, managing an MFA device for our users. So again, I'm logged into the console. I'm here at the Identity and Access Management dashboard. And what I want to do in this example is to add an MFA device, multi-factor authentication, for a particular user. In this case, we're going to use the Jane Doe user that we've created. So I'm going to click through to that user's details. I'm going to scroll down, make sure that I'm on the Security Credentials tab. I'm going to scroll down, and you can see that Jane Doe does not yet have a multi-factor authentication device listed. So you can see here that we have two options. We can use a virtual MFA device that's for an application on a smartphone, or we can use a hardware MFA device. Now, in order to use the hardware MFA device, and again, the hardware option is recommended for your root account, and you would have to order that hardware MFA device directly from Amazon. In this example, we're going to use a virtual MFA device. That would be, there are a number of different applications available for smartphones, such as Authy or Google Authenticator, just to name a couple. So I'm going to click that, hit Next. Yes, I understand that it is for a smartphone. I'm going to click Next, and you can see from here, it gives us this particular QR code that we would use the application on our phone to scan this, and then that application will automatically configure that MFA code. I could alternately, for some other applications that don't have the ability to scan that QR code, I could show the secret key and then just copy and paste that and put it into the application. And then of course, in order to be able to use this device, what we would do is we would implement the authentication code twice. And from there, once we have those codes, we could then activate that virtual MFA. Okay, so from here, I'm going to use the application on my smartphone to scan this particular QR code. And then once I've got that done, I want to take the codes from that device I'm going to add the first code here and then wait. It's going to take a few seconds, up to 30 seconds. Every 30 seconds the code rotates to another one. So in order to activate this MFA device, we need to put in 2 consecutive codes so that it ensures that we actually have it configured correctly. So the next code that comes up would be this one here, 2 codes, and it ensures that both of them were correct, and now I have the multi-factor authentication configured correctly. So now, and of course I would have done that on Jane's phone. In some organizations, sometimes if it's a small team, I might just have Jane come over to my desk and have her use her phone to scan that QR code and set up the MFA. In larger organizations, that's perhaps not feasible, especially if you are dealing with people that are remote. And so in those situations, you want to give those users permission to manage their own MFA device. Now, it's important to, in some cases, deactivate an MFA device. If, let's say that Jane lost her phone, that's a really good time to come in and deactivate that so that whoever picks up her phone can't go and start using her MFA device. So in that case, we want to be sure to click that and deactivate. It's pretty rare for virtual MFA devices to have to be resynchronized, but for physical key fobs, sometimes you have to do that. But in this case, if considering that Jane may have lost her phone, I want to deactivate that. I'm going to choose deactivate, click next, and now the MFA device is gone. So that's how we manage an MFA device for a user within Amazon Web Services Identity and Access Management. So now let's review resource policies within AWS. So now resource policies are a slightly different way of applying permissions to our AWS resources. The policies that we talked about earlier as a way to grant our users permissions to do things within AWS were policies that were meant to be applied directly to a user or a group of users. But what we're talking about here, resource policies, are policies that are meant to be applied directly to a resource, such as an Amazon S3 bucket. In that example, you might want the bucket to grant permissions to the world at large, to anonymous users, people who don't necessarily have an AWS account. So we would do that on the actual bucket. And that's a great way to make an S3 bucket publicly readable. We can apply resource policies to Amazon DynamoDB tables and make those tables publicly readable. We can apply them to the Amazon Simple Queue Service queues as well. And this is just 3 examples of the possibilities that we have with resource policies. A number of AWS services support resource-based policies. They are essentially the same as the policies that we've already seen. They're written in JSON. We can provide cross-account resource sharing if we want to. If we have an S3 bucket in one account, we can allow someone else's account to leverage that bucket if we want to. We can also, as I mentioned, allow anonymous use. Again, resource-based policies are essentially the same as the policies that we've already talked about, except they're not applied to a user or a group of users. They're applied to the actual resource itself. Okay, so now let's walk through a demo of applying a resource policy. Again, I'm logged into the console. From here, this particular demo, I'm going to apply a resource policy to an S3 bucket. So from here, I'm going to go to the S3 service. And you can see I have a number of buckets that I've created over time for various different projects. In one example for this demo, we're going to take a look at my talentedmrjones.com bucket. So this particular bucket is where I host my talentedmrjones.com website. I have this bucket configured to host a static website, but there's one thing that I need to do in order to allow anonymous users the ability to read things from that bucket. So I'm going to click through to that bucket, and I'm going to click on the properties of it. So I'm looking at the properties of the bucket itself. You can see I have a number of different objects within the bucket. And in order for anonymous users to be able to read this, I need to go to permissions and add a bucket policy. So from here, I'm going to add a bucket policy. Now, I could copy and paste in here if I already had it available, which I don't. So I'm going to click the policy generator. And from here, you can see that there are a number of services that allow us to create, and these aren't all of them. There are other services that allow us to create resource-based policies. I'm going to choose the S3 bucket policy. I'm going to put star for anyone. That means essentially anonymous users. Everyone is allowed to, I'm going to choose a very specific action here called getObject. Just that one action will allow them to download an object if you already know about it. If you don't, if you want to list the contents of the bucket, that's a completely different permission. In this case, we don't need them to do that. All we need is to allow them to download particular objects. So I'm going to choose that one. I'm going to say that they're allowed to do this on this particular bucket. Not any bucket, but this one. So I'm going to say ARN:, AWS:, S3. I don't need the regions and account numbers and things like that. I'm going to say 3 colons, the name of the bucket, talentedmrjones.com, and then it's very important here at the end that we're not talking about the bucket itself, but objects in the bucket. So /star in this case will allow the user to download objects within the bucket. So I'm going to add that statement. You can see here we're allowing everyone, anonymous users, the ability to download objects from S3 from anywhere within this particular bucket. So I'm going to go ahead and generate that policy. I'm going to highlight, copy, come back over here to the S3 console. I'm going to paste that here, and I'm going to click Save. And you can see the little green check that came up there. The fact that we got that green check and this went away means that the policy is valid. And now you can see that this has changed from add bucket policy to edit bucket policy. And that is how we create and apply a resource-based policy. Again, we've done this on an S3 bucket, but we could very well have done this on a simple queue service queue, a DynamoDB table, or various other Amazon services. Okay, so now let's review a use case, using roles for cross-account access. So in this use case, what we're looking at are leveraging multiple accounts in one organization, multiple AWS accounts. And this is a very common practice. A lot of organizations will do this, split up different resources between different accounts. This is also considered a best practice and recommended by AWS to do this. Now, how you split your resources up between accounts is totally up to you. This is just one example. You don't necessarily have to do it this way. But in this example, what we're going to do is put our development resources over here in what we might call a development account. And that's completely arbitrary. That's just what we've chosen to name it. Again, there's nothing in Amazon Web Services that says we have to call it that. We're going to put our production resources in a production account. Now, the key here is what we call the payer account. So our initial account that we open, we might call that the payer account. And within that account, again, we will have no users, no groups, no roles. We will have no resources deployed. And the only thing that we use that account for is for paying the bill. So again, that's what we call the payer account. The other two accounts are what we call the linked accounts. These are the accounts in which we create and manage our resources. And of course, again, the payer account is just the account we use to pay the bill. So again, here in the development account, just one way to use this is here we would add our users, our groups, and our roles. We would add our development resources. And in the production account, we won't have any users. So no users or groups. In order to get access into production, we will leverage roles, and we're going to review an example of how to do that coming up. Now, the way that you link these accounts are completely up to you. You might separate further into different types of environments. You might have an account for QA, an account for testing. You might split them by department or business unit. Perhaps you want finance and accounting resources in one. You might want engineering or research and development resources in another one. Again, it's completely up to you. Now, moving forward from this example, what we're going to look at is how this actually continues to work at the user and role level. So in our development account, we have our user. In this particular case, our user is Jane.doe. And in our production account, notice we have a separate account number up here. We have a role. So again, in our production account, and in this particular example, we will not have any users over here. We just have a role. So when Jane wants to do things, perform actions on production resources, what she will need to do is assume a role in order to do that. So here we have a role called admin. You can see that this role, in this particular example, it's allowed to terminate EC2 instances, but only in perhaps a particular region, whatever region that is. Maybe it's only in US West and not US East. We also have what we call a trust relationship. Essentially what we're saying is that when we create this role for cross-account access, we're going to specify that we are trusting, again, we're trusting the development account as an account that we allow to assume that role. What we're also going to do is give this user, we're giving Jane Doe the ability to assume that role. So you can see here that we're going to allow her to assume that role. And notice that we are specifying here the account number of the production role. So again, what we have is a user in our development account is assuming a role that is trusted by the production account. And once Jane Doe assumes that role, she will then be allowed to perform these actions on resources within the production account. So let's look at how this actually works. Our user, Jane Doe, in this particular example, will use the AWS command line tools to assume this particular role. So we're using the STS service, the security token service, and we're calling the action assume role. And as we've seen, we've already given the Jane Doe user the permission to perform this particular action. So she's calling the security token service saying, I want to assume the admin role in the production account. The security token service will return, again, temporary credentials to the Jane Doe user. Then she can use those temporary credentials to perform another action. In this particular case, perhaps Jane has determined that she needs to terminate a particular instance in the production account. So again, she might use the AWS command line tools, leveraging the EC2 service to terminate instances, leveraging these temporary credentials. And in doing so, she can then terminate this particular EC2 instance. So again, that's just one example of leveraging roles to allow a user in one account to access resources in another account. And perhaps you do that, it could be an account that you own, it could be a third-party account, such as a customer or a vendor as well. So again, using roles for cross-account access are a really powerful and flexible way to achieve a higher degree of security within your Amazon Web Services environment. Okay, so now let's review some best practices within AWS Identity and Access Management. It's really important that we leverage groups, especially when we have a large number of users. It just makes life easier when you go to assign permissions to different groups of people. Grant least privilege, meaning that give a user the enough permission to do what they need to do, but not so much that they can be dangerous. We need to implement strong password policies, including allow them to be long, make them use multiple types of characters like numbers and special characters, deny the last 3 passwords being reused. In a larger environment, it's also really helpful, and it adds that extra layer of security by leveraging multiple accounts. So divide your organization into multiple accounts, whether it be development versus production or one business unit and another business unit. It doesn't really matter, but leverage those multiple accounts and leverage roles for cross-account access. If you want to add another additional layer of security, use deny statements, because again, as we've talked about, deny statements, the way that the evaluation logic works, deny statements cannot be overridden by an allow. So using deny statements just means that you have extra guardrails, that no matter what, that user will never be allowed to do something unless you go in and remove that deny statement. Never share your credentials. When you create access keys, usernames and passwords, don't share them, don't email them, don't print them, don't put them into your code repositories. and again, leverage those multiple accounts. Now, in regards to our master account, when you first create your AWS account, that initial email and password is going to be your master account. It's considered root, or if you're a Windows user, it's considered administrator. It has an implicit allow all that cannot be changed. You have no control over the permissions of that root account. It's allowed to do anything on any resource at any time from anywhere. So it means that that account is incredibly powerful and incredibly dangerous if that account is compromised. So we need to protect that master account at all costs. And I say that because companies literally have gone out of business by allowing their master account to be compromised. Hackers have gone in and hijacked those credentials. They've asked for ransom in some cases, and in other cases they have deleted production resources to a degree that caused that business to go completely insolvent. So never use it for day-to-day. The master account will come with default access keys. We want to delete those so that they can't be compromised. We want to enable multi-factor authentication with a physical key fob, not a virtual one on your cell phone or your smartphone, but a physical key fob that you then lock in a safe. And I'm not kidding on that point. It's so incredibly important to protect that master account at all costs. I do that with my own business, and I've done that for clients of mine by enabling MFA and locking it in a safe. Another thing that you should do is go and read the security white paper. It's probably one of the most popular white papers available on the Amazon website, and you can see it here at the link. So again, protect that master account at all costs and be sure to read the security white paper. Networking in Amazon Web Services is perhaps one of the most important aspects to learn and become proficient at because it fundamentally affects everything you work with, from virtual machines to databases, high availability, security, and more. To a seasoned IT professional, many things in AWS will be familiar, yet many things will also be new concepts or work in significantly different ways. So in this lesson, we will cover Amazon Virtual Private Cloud, subnets, routing, firewalls, and much more. All right, so let's take a look at Amazon Virtual Private Cloud. Amazon Virtual Private Cloud is a way to give us essentially our own private networks within Amazon Web Services. Typically, our applications need some kind of predictable IP address range. We need to know where they're going to fall. When these machines come up, we need to know the kinds of ranges that they're going to get so that we can determine routing and firewalling rules. We want to segment our networks in terms of some networks need access to the internet, meaning they need to be public. Some networks need to remain private. We only want them to be available either internally or via some kind of a VPN or between different private networks. We need the ability to control what ports are open and what ports are closed. So in the case of a web server, let's say that we have some kind of a web application running on an EC2 instance, then we might want to allow common HTTP and HTTPS ports to be open. Our database should probably allow port 3306 open, but we want to block all other ports from this untrusted network. So we need the ability to allow our web application to receive public traffic, but we might also want to keep this database private and not allow access directly from the internet. And we can do that and more with Amazon Virtual Private Cloud. So with Amazon Virtual Private Cloud, what we would do is we would create a VPC in a particular region. We're going to choose, in this case, we're using US West 2 in Oregon. And we're going to, at the time we create that VPC, we're going to choose a particular address range. Now, in this particular example, we're using 10200/16. So that's a pretty large range. That's the largest range that we can choose within Amazon Web Services. We can go as small as a /28, as well. So it's important to note that when we divide this network up into subnets, you can see here we have 3 subnets, 1 per availability zone, that subnets are specific to availability zones. The VPC itself will span the entire region, but a subnet will be specific to an availability zone. So when we go to launch virtual machines, we don't choose the availability zone directly. We choose the subnet we want that machine to be in, and through this subnet and the availability zone association is how we determine where that machine will actually be launched. So you can see here that when we create subnets, we have to be sure that our subnets don't have any kind of IP address overlap. So our first one would be 10.2.0.0/24. That would give us somewhere around 250 usable IP addresses. The next one is 10.2.1.0/24. So again, we want to make sure here that we're not getting an IP address overlap. And of course, the last one, you can see we chose a slightly different range with a /28. Perhaps we want web and application servers up here and these subnets, and we might reserve the last one for databases, and we don't really need that many IP addresses, so we chose a smaller range. So again, Amazon Virtual Private Cloud is a networking construct. It allows us to create private networks. It allows us to divide those networks into subnets, whereas each subnet is specific to an availability zone, and the VPC itself spans the entire region. All right, now let's run through a demo where we'll create a VPC. You can see that I'm logged into the networking. Console. From here, I'm going to, now I could scroll down here to the networking section, or from the top, I could click the services menu, and they would be listed, all of the services are listed alphabetical. So there is VPC on the right. I could also come here to networking and choose VPC. So I'm going to go there to VPC. Now, here at the VPC dashboard, you can see I have 1 VPC, I have 1 subnet, 1 NACL, 1 internet gateway, and 1 route table. Now, one thing I want to point out here, you can see I have a VPC here in this particular region, in the Oregon region. Remember that VPCs are specific to a region. The subnets inside of that VPC will be specific to the availability zone. So you can see I have 1 subnet already created. Within this region, I've already deleted the default VPC. So I'm going to switch regions just real quick to show you. I'm going to switch over to the Ohio region. Doesn't really matter, any region would do. And you'll see that here is what we call the default VPC. This is default because it comes with your account. As soon as you create your account, you already have this default VPC. Amazon does that as a way to just lower the barrier to entry. It makes things a whole lot easier, especially for developers and folks who don't have a whole lot of knowledge and experience with networking. They just want to launch EC2 instances and get something running. So the default VPC is there for that reason. But I want to create one with a different IP range and have a bit more control over how it's actually created. So from here, I'm just going to say create VPC. I'm going to name it AWS Live Lessons. Perhaps we'll put some applications in here later. Now the CIDR block, this is up to us. And generally when we're creating VPCs, depending on how we want to segment between applications or department, we need a strategy for handling our ranges. So for this one, I'm just going to choose something like 10.2.0.0/16. Probably a whole lot more IP addresses than I'll need, but that's okay. So I'm going to hit create. And sometimes it takes it a few seconds to create that necessary resource. You will see that here I have 2 VPCs now. The default VPC, which is always 172.3.1, and then of course the VPC that I just created. we could go over here and filter by VPCs. I'm going to choose that one, and you'll see now, because we're filtering, that only the VPC that I just created shows up. You will see now that this VPC does not have any subnets. It does have a default route table. So if we look at that, we will see that we are routing the 10.2.0.0.16 to local within the VPC. So that's essentially our default route table. We will also see that down here are network ACLs, that we have a network ACL for that VPC, and the network ACL that we get by default allows all incoming traffic and allows all outgoing traffic. So that is creating a VPC within Amazon Web Services. All right, so now let's run through a demo of adding a subnet to an existing VPC. So here we are, logged into the AWS console. I'm on the VPC dashboard. And what I want to do is filter by the VPC that we recently created. In this case, the one at 10.2/16. And then from there, I'm going to go to subnets, and you will see that we don't have any for this VPC yet. Now, it's important to note that you can't launch resources such as EC2 instances, virtual machines, or databases directly into a VPC. You have to have a subnet in order for resources to have a place to live in the network. And so we're going to create a subnet. Now here, I might call this one our public A, because I'm going to put this one, you'll notice that I'm going to choose an availability zone here. Again, subnets are specific to an availability zone. So this one is going to be my public subnet in US East 2A. US East 2 being the Ohio region. Now, when I set the CIDR block for that subnet, it has to fall within the range of our VPC being 10.2.0.0/16. I could create a subnet that takes up the entire range of the VPC if I wanted to, but by doing so, that would prevent me from creating any more. And that's not what I want to do. So here, I'm just going to do 10.2.0.0/24. That would give me somewhere around 250 usable IP addresses. So I'm going to go ahead and create that. Again, sometimes it takes it a few seconds. Shouldn't take no more than a minute. There we go. And now you can see that we've created a subnet. We can see what VPC it belongs to. It belongs to our AWS Live Lessons 10.2.16 subnet, and this subnet has this particular CIDR range. Now, you might be wondering, a /24, if you're familiar with CIDR notation, you would know that /24 would allow up to 256 IP addresses. It's important to note that the first four, for any given subnet, the first four and the last one address are reserved by Amazon for special purposes. The last address being the .255 is the broadcast address, and that's not used by AWS, so they reserve it. The first four are reserved for special purposes like routing and local VPC DNS. So we have a subnet in the US East 2A availability zone, and we'll go ahead and create one more just to run through it one more time, and I'm going to call this public B. Again, this is arbitrary. What you name it is up to you. It depends on what this particular subnet is being used for. I'm going to make sure that I have the right, I don't want the default VPC, I want the one that I created recently. In this one, I'm going to use 2B availability zone, which again is a completely different set of data centers somewhere down the road away from 2A. In this case, I'm going to use 10.2.1.0 so that I don't overlap with the previous one. Again, /24, and create that as well. So there we go. We have our two subnets that we've created, public A and public B. Here we'll talk about routing within Amazon Virtual Private Cloud. So routing is the method by which we can control the flow of traffic within our AWS Virtual Private Cloud or our private networks. So, and let's take a classic three-tier architecture where we might have a load balancer out front accepting public traffic coming in from the internet. We might have an application server in the background. We also would have that communicating to a database. Now, in that situation, we would want to keep our application servers and our database servers private. We don't want people to be able to come in from the internet and get access to those directly. We might also want our database to communicate back to our on-premises network over a VPN, a secure connection, so that we can do various administrative tasks. So the way that we control that flow of traffic is by way of route tables. So what we want here is this subnet to have access to the internet. And we can do that with a route table. So we have a route table with, you can see here, a couple of route entries in there. The one by default, you'll notice here, 10200/16, matches the address range of the VPC. So that means that any IP address in this range as a destination will be routed locally throughout that VPC. The next entry, you can see here we're using all zeros. That's the widest open range we can possibly use. That essentially says that all other traffic will be routed to an internet gateway. Now, an internet gateway is a separate device that we create and attach to our VPC so that we can get bidirectional internet traffic. And that's important to know that when I say bidirectional, we mean that resources within this particular subnet can not only reach out to the internet, but devices out here on the internet can also reach in. And that's important to know because it means that devices here, in order to communicate to the internet, will have a public IP address and they will be reachable from folks on the internet, good folks and folks that might be nefarious. And so that's why we have routing. We want to control the flow of traffic so that those malintended users can't get access directly to our application servers and database servers. In this example, we would allow our application servers to use the default route table that just maintains local traffic. We would create a new route table for our databases so that we have this additional entry. You can see here again, we have local traffic routed locally, and then we have our on-premises network range 192.168/16 routed over our VPN. And again, we'll talk about how to create VPNs later. So here, our database administrators can, from the on-premises network over a VPN, get in and do what they need to do on the database. Our application server can communicate to the database locally, and our load balancers can communicate to our application servers locally. So again, routing is how we control the flow of information and how we control the flow of traffic between different subnets, between our network and the internet, and between our network and VPN connections. So here, let's review a demo of routing our subnets to the internet. Again, back in the console, I'm going to make sure that we are filtered by the VPC that we're working with, in this case, the 102/16. From here, I'm going to go to my route tables, and you will see that we have one route table. This is what we call the main or the default route table. You'll notice that it is where we say subnet associations. It says 0 subnets are explicitly associated. That means that these particular subnets, because they don't have a route table directly associated, that they are falling back to this route table as their default. That's what makes this the main route table. So what I want to do if you'll notice here that the route that we have is local. And what I like to do is keep the main route table, the fallback route table, private, so that we don't end up inadvertently giving public internet access to subnets without realizing it. So the first thing that I want to do is I'm going to create a new route table, and I'm going to call this one public traffic. And again, I want to make sure that we're using the right VPC here, not the default, but our 10.2. Wait for that to create. So now we have our public traffic route table. You can see that it is not considered the main route table, and again, it doesn't have any explicit associations. But we do want to associate this route table with our two subnets that we created that are meant to be public. So I'm going to edit that and make sure that this particular route table for public traffic is associated with those two subnets. I'm going to save that. And there we go. Now you can see that this particular route table is explicitly associated with these two subnets. That means that those two subnets will use whatever routes we specify here in this route table. So we have our route tables attached. Now in order to get traffic to and from the internet, one more thing that we need is an internet gateway. We don't have any for this VPC yet, so I'm going to create one. Again, I'm going to call this one AWS Live Lessons. Sometimes it takes a second for that to show up. There we go. So what we needed to do was undo our filter because this internet gateway is not attached to a VPC yet. So I'm going to highlight that, and I'm going to attach that internet gateway to the appropriate VPC, in this case, the 10.2. I'm going to go ahead and click Yes, Attach, and now you can see that not only do we need to create the internet gateway, but we also have to associate it or attach it to a VPC. Now that that internet gateway is available to our VPC, we can go back to our route tables. I'm going to, again, filter by VPC. I'm going to choose this public traffic route table, and you can see that we only have local traffic. I'm going to edit that, add another route, and in this case I want to say all zeros. And you can see here, just by clicking in there, gives me the option to choose the internet gateway that we just created. So this particular route says that essentially all other traffic should be routed to the internet gateway. So I'm going to save that. Now there is one more thing that we need to ensure. In order for virtual machines within these public subnets here to actually communicate with the internet, they need the internet gateway to be attached to the VPC. They need a route table and a route entry that actually says traffic can flow. You can see here that we have that route entry in that route table. The other thing that they need is a public IP address. Now we can get that here. We can say modify auto assign public IP. And I'm going to check that so that when we launch EC2 virtual machines, or EC2 instances as we call them, into that subnet, we can choose for that EC2 instance to automatically get a public IP. If you don't do that, if you end up launching an EC2 instance without a public IP, it will not be able to communicate with the internet. So I'm going to do the same thing here on the other subnet. Again, I'm going to modify that, enable auto assign public IP, and hit save. And that way, any EC2 instances that are launched into those subnets will receive a public IP, and their traffic will be routed through the internet gateway to and from the internet. And that is how we route traffic to the internet in AWS Virtual Private Cloud. Now let's talk about what we refer to as public, private, and hybrid subnets within AWS VPC. Now, there's nothing necessarily within AWS that you will find that inherently labels a subnet as being either public, hybrid, or private. These are terms that we're adding just to denote the types of routing that are possible. What we might call a public subnet is a subnet that has a route table that gives us access to the internet. So like we've seen before, we have a route table, and this route table would be attached to this particular subnet. And that route table, by way of this open range and routing to an internet gateway, would give us a bidirectional access to and from the internet. So that would be a public subnet because it has access to the public internet. As we've also seen before, we might keep some of our networks private, meaning that there are no additional entries in this route table. The only thing we have is local traffic. Now, what might create a hybrid network is where we might have our application servers here that need to reach out to the internet in order to do things like, posting to a monitoring service, posting to some kind of something like PagerDuty or Loggly, where we're sending logs, we're sending alarm notifications. And so we need to get out to the internet. Maybe we want to do patch updates and software updates. We want to connect to GitHub. Whatever it is, our application servers need to communicate with the internet, but at the same time, we don't want people coming in from the internet directly to our application server. That's just bad security. So in this particular example, what we're going to do is we would have a NAT server, or a network address translation service. This is also a resource that we can create within AWS here in the public subnet. And so the network address translation server has access directly to and from the internet and can send and receive traffic directly to and from the internet. And then our application server would essentially route all of its internet destined traffic through the NAT server. And we can do that by way of this kind of routing. Notice that we have another route table that would be attached to this particular subnet. And so that we would say, aside from local traffic, all other traffic gets routed to the NAT gateway. So not only can we route to devices like an internet gateway, we can also route to other EC2 instances. So in this particular case, our NAT server could be the Amazon service. It could also be something like a virtual F5. It could be a virtual Viata server. It could be just software running on an EC2 instance if we wanted to do it that way. And we would route this traffic to the NAT gateway, and that way our application servers can reach out to the internet but are still protected from malicious users coming in directly. So again, public subnets would be considered public because they have access to the internet. Private subnets are considered private because they don't have access to and from the internet. And hybrid subnets are simply private subnets that have outgoing access to the internet by way of a network address translation server. Now let's take a look at network access control lists, otherwise known as NACLs. Security of our environments, security of our networks within AWS is paramount, and one of the tools that we have access to are network access control lists. These are like firewall rules, but they are applied to a subnet as a whole. They're not applied to individual EC2 instances, but they're applied to the subnet, no matter what EC2 virtual machines or how many are in there. Another thing to keep in mind is that a network access control list is stateless. That means that if something comes in as an initial connection and then packets go out in response, the network access control list will not recognize those packets as being in response. And so the side effect of that is that we have to specify both ingress and egress rules in order for traffic to flow. Now, with NACLs, we can specify both an allow or a deny. They actually do default to denying all, and of course we can override that with our rules. We're going to specify the protocol being either TCP, UDP, ICMP, or all traffic. We will specify an IP range where traffic is coming from and a destination port range. Let's say that we have an application web server, and this web server needs to receive traffic on port 80 and port 443. So we're going to say that we're going to allow these two ports to come in from anywhere. And this would essentially apply to the internet. We don't know where they could come from. They just need to be able to allow anywhere. We want to restrict port 22 from our corporate VPN. So here we're going to specify a much narrower range, being 192.168/16. So perhaps this is the range of our corporate VPN. Now, if traffic is coming in on port 80 or port 443, it's important that response traffic be able to go out. Now, typically in a web server use case, that outgoing connection will be on a different port. It'll go back on a port range, somewhere on an ephemeral port within a pretty wide range, 1024 through 65535. So in order for the response traffic to be able to leave the subnet, we have to be sure that we allow this range of ports, being the ephemeral port range. So again, network access control lists are a very key tool that we should be using within virtual private cloud. They're applied to a subnet as a whole, and remember that they're stateless. We have to specify ingress and egress rules. So again, to reiterate this important point, that network access control lists are applied to the subnet as a whole. So in this particular example, let's say that we have our web servers here, and we have our databases back here in another subnet. So we can see that we have our network access control list applied. It's sort of like, you can imagine it like a firewall around the entire subnet. And in that last slide, we can see that port 80 is open from pretty much anywhere. So traffic coming in on port 80 would be allowed to pass through. Here, it's allowed to pass through the NACL. Port 22 is not allowed, but it is allowed from our VPN. So as long as we come from a range, 192.168 range, then that port 22 traffic would be allowed through the NACL and into the subnet. Now, in the case of having database servers in another subnet, we would probably want a NACL that allows port 3306 to come in from our corporate VPN range, perhaps 192.168 to come in, but the NACL itself would block all other attempts or all other sources on that particular port. We might also even deny and say that port 3306 is allowed through the NACL from the range of our application servers, but nowhere else. If we had other subnets in this particular VPC that were being used for different purposes, then we might also want to block port 3306 from those ranges and only allow it from the range of our application servers. So again, network access control lists, you can think of it as a firewall for the entire subnet. It prevents traffic from getting into the subnet. And then, of course, we have other means that we'll talk about later on as a means to limit the flow of traffic on a per machine basis. Now let's talk about security groups within AWS VPC. Now, security groups are another tool that we have access to within AWS VPC that allows us to create a secure network. We've talked about routing as a way of controlling the flow of traffic. We've talked about NACLs as like a firewall around the subnet as a whole. Security groups are like a firewall around specific EC2 virtual machines. So whereas a NACL is applied to a subnet, a security group is applied to individual instances. Where a NACL is stateless and does not remember traffic being in response, a security group is stateful. It does recognize traffic as being in response to something. And what that means is that you don't have to specify both ingress and egress. You can specify one or the other. Very much like NACLs, we specify the protocols being TCP, UDP, whatever it is. We specify our source IP range and our destination port range. In this example, kind of picking up from our previous example where we were using a web application server, we want to receive traffic on port 80 and 443 from the internet. So we want to make sure that this particular instance, this virtual machine, is allowed to receive traffic on these two ports from anywhere. These all zeros meaning essentially anywhere. Now here's an example of receiving, perhaps this is some kind of an application port, a special port we're using for monitoring, whatever it is, and we want that to be allowed from another particular instance. Here we can use, instead of an IP range, we can use the ID of another security group. So that means that this traffic is allowed on port 9999 as long as it comes from a machine that has this particular security group applied to it, and we call that a reference. It is a reference to another security group. As we saw in the previous example about network access control lists, even though the NACL allows port 22, we still have to allow it. That gets it into the subnet, but in order for those packets to get into the virtual machine, that port also has to be open in the security group as well. And so we're also going to say that port 22 is allowed, but we want to limit it to our corporate VPN at the range of 192.168/16. Here's the key difference between security groups and NACLs, being stateful versus stateless. If you recall, when we talked about NACLs, we had to explicitly open, in order for response traffic on HTTP and HTTPS connections to get back out. On the NACL, we had to specify the ephemeral range ports for egress traffic. We don't have to do that here in a security group because security groups are stateful. They will recognize that outgoing traffic is in response to packets that were initiated on port 80 and 443. So the only time we really need to specify egress rules are when we're talking about initiating connections. And so here what we're saying is that whatever machine this security group is applied to is allowed to make initiating connections on port 3306, being to MySQL, so long as those connections are being made to a machine that has this security group applied to it. Any other machine in the network that does not have that security group applied, this port will not be allowed to go out. So again, that is considered a reference when we mention the security group ID rather than an IP range. So again, to recap, network access control lists are stateless and applied to a subnet. Security groups are stateful and applied to individual EC2 instances. So here's another example, another way to look at that, another way to look at the relationship of security groups is that security groups, again, you can see that they're applied to the instance itself, not necessarily to the subnet as a whole, but to the instance itself. This one has a security group. This other EC2 instance has its own security group. Perhaps we might want to allow remote JMX monitoring on port 7199. We want to allow HTTP and HTTPS ports coming in from the open internet, so it'll be allowed into the security group. We're going to allow this security group to initiate connections on port 3306 to our database. So port 3306 will be allowed outbound as an initiating connection, but everything else will be denied. Now, response traffic to to HTTP and HTTPS traffic will be allowed, but it's only the initial packet that we're blocking here in this example. Now, our database would also allow port 3306 to come into its security group so long as that traffic originated from this security group over here. Here, let's review a demo of creating and applying a network access control list to an existing subnet within VPC. So again, we're back in the AWS console. In the VPC dashboard, I'm filtered by the VPC that I want to work with, our 10.2/16. We have created some subnets, as we can see here. We have created some route tables and internet gateways. We have traffic routed to and from the internet. But now we want to tighten security around those public subnets. Perhaps those public subnets are meant to house a web server. We don't need port 22 open. We want to put some guardrails around that subnet so that the subnet as a whole is protected from system ports like port 22 and so on from being accessed from the internet. So I'm going to come down here to network ACLs. You can see that we get a default NACL where all traffic is allowed, both inbound and outbound. Now from here, I want to create a new network ACL. I'm going to create a new one. I'm going to call this one public or perhaps web traffic. Again, I want to make sure that we're using the right VPC. Now that it's created, I need to associate that network access control list with the subnets on which I want to control ports. So here I'm going to edit. I'm going to associate this with both of our public subnets. I'm going to hit save. Now that we have our network access control list associated with our subnets, we can go back and start to modify our inbound rules. Again, you can see that because this was not the default NACL that came with the VPC, it's defaulting to denying all traffic, both inbound and outbound. So now that this particular NACL is associated with our subnets, no traffic can enter or leave those subnets. So the first thing that I want to do, considering that this is meant for a web application, for inbound traffic, I want to allow, I'm going to say, I'm going to start with rule number 100, and I'm going to choose HTTP traffic, or port 80, which is TCP port 80, and I'm going to allow that from the internet using all zeros. I'm going to add another rule, 101 being HTTPS here, which is TCP port 443, and again from the internet. And I'm going to save those two rules. Now you can see that those packets are allowed into our NACL, and all other traffic is still denied. So port 22, port 21, whatever, all other ports are denied. Now, as we've talked about, network ACLs are stateless. We have to create both inbound and outbound rules. At this point, our web server would be able to receive a connection on port 80 or 443, but the response traffic would not be able to get out. You can see here that outbound or egress rules are still being denied. So from here, we don't really need these machines, these web servers, to initiate connections on port 22 for SSH or port 21 for FTP. That's not their purpose. So we're going to allow ephemeral ports. I'm going to say rule number 100 will allow all TCP on port 1024 through 65535. That is essentially, in all practical reality, that is the ephemeral port range. And we're going to say that those port ranges are allowed to go out to anywhere because we're going out to the internet, where we are allowing that range. I'm going to go ahead and save that. And now you can see we have created a network access control list. We've associated it with our two public subnets. We have allowed port 80 and 443 to come in, and we have allowed the ephemeral port range to go out. And that is how we create and associate network access control lists within AWS VPC. Now let's take a look at another demo where we'll create a security group within AWS VPC. Okay, so from the dashboard, the AWS console, again, I'm going to filter by the right VPC. And so far, we have created a VPC, we've created some public subnets, we've routed them to and from the internet with our public traffic route table. We have created a network access control list for web traffic, tightened the security for that. You can see we're allowing HTTP and HTTPS traffic into that subnet and allowing ephemeral ports out. Again, just as a reminder, network access control lists apply to the subnet as a whole. We still need a way to secure the instance itself, a firewall for the individual machine. And we can do that with security groups. So this particular VPC, like all VPCs, will come with a default security group, but it's generally best practice to create security groups per purpose. So for a web server, we have a web server security group. For an application server or database server, they each get their own specific security group that's more specialized to what that machine is actually doing. So from here, I'm going to click Create Security Group. I'm going to call this one Web Server. I'm going to describe this as Web Application Security. Make sure that we're choosing the appropriate VPC and create that. Now that we have the web server, you can see here we have our web server security group. So far, by default, we do not have any inbound rules. That means that whatever EC2 instance this security group is attached to cannot receive any traffic until we open this security group up. So I'm going to edit that. Again, I'm going to allow it to receive HTTP traffic from anywhere. I'm going to allow it to receive HTTPS. And again, I'm going to choose from anywhere. I'm going to save that. Now, whatever EC2 instance we apply this security group to will be allowed to receive traffic on port 80 and 443. It might seem like we're doing double work, but we're doing things for different purposes. We've added very similar rules to the NACLs so that our subnet can receive traffic. We've added these same rules to the security group so that our instance can receive traffic. Now, as a reminder, the difference between NACLs and security groups is that the NACL was stateless. That's why we had to specify both inbound and outbound rules. The security group being stateful means that we don't have to specify outbound rules. And again, that is for response traffic. If a request comes in on one of these two ports and then the response goes back out, the security group will allow that, so we don't really have to mess with outbound rules. I do want to point out that security groups by default do allow all outbound traffic to all destinations, but what this is talking about are the initiation packets, that initial connection. It's not talking about response packets. So that is how we create a security group within AWS VPC. So here let's talk about VPC peering within Amazon VPC. VPC peering is a way of connecting two VPCs, two private networks. So it's really helpful when you want to segregate networks for different purposes. Perhaps you want your applications in one network, your databases in another. Perhaps you want, one business unit to have their own network and another business unit to have their network. So that's up to you. It's just a matter of how you want to segregate your networks. There's no bottlenecks, there's no single points of failure. It just happens. Amazon handles the peering connection for you. So you can peer VPCs within your account, you can peer VPCs across accounts as well. Those can be accounts that you own, or they could be third-party accounts like clients or vendor accounts. The important things to keep in mind is that IP ranges between VPCs cannot overlap. They are always one-to-one, no transitive peering or edge-to-edge routing. And what that means is, if we have virtual machines here within VPC A, those virtual machines cannot get to virtual machines over here in VPC C by going through B. That would be transitive peering, and you can't do that. If we have machines here in A and they need to talk to machines over here in C, we would have to establish a one-to-one VPC relationship between A and C. Now, in order to peer two VPCs, first what we need is what's called the peering connection. Here, the peering connection is a resource in and of itself that we create through various means, one being the AWS console. So we would create the connection, and in doing so, we would choose the two VPCs that we're going to peer. In this case, we have one at 10.2.0016, and we have another one over here at 10.6.0016. So it's important to see that, again, we are not overlapping our IP ranges. Now, when we peer these two VPCs, again, this peering connection is managed by Amazon. There's no network bandwidth bottleneck. There's no single point of failure. It's a very stable device that we can count on. It's attached to our VPCs. And in order for traffic to flow, we have to have, like we've talked about, we have to have routing in place. We have to tell Amazon Web Services how to route our traffic. And we can do that in one of two ways. We could either route the entire VPC. Notice the entries in our route table here. We have from 10.2, we want traffic destined for 10.6 to be routed to our peering connection. Conversely, over here on our 10.6 network, we want traffic that's destined for 10.2 to also be routed to our peering connection. So we essentially have our two route tables and our two routes that are pointing towards each other by way of the peering connection. And that's an example of routing the entire VPC. In other cases, you might not want to route the entire VPC. In other cases, you might want to route just very specific subnets. And so you can do that as well. Here, perhaps we only want to link the 10.6.1 subnet, this one here, with the 2.1 subnet. And you can see here that we're saying traffic destined for 10.6.1 is routed to our peering connection, and on the other VPC, traffic for 10.2.1 is routed to the peering connection. Peering two VPCs is a one-to-one relationship. There's no transitive peering, there's no edge-to-edge routing. It's a one-to-one relationship by specifying peering connection and routing traffic from one range to another range. Now let's take a look at a few VPC peering scenarios. There are many ways that you could segregate your networks, separate applications and departments, and peer VPCs using different strategies. One strategy might be that you want to isolate different services. In this example, we might want our web application in one network, all of our backend servers in yet another network, and then our databases in their own network. This is totally up to you. It's fairly arbitrary. There's nothing within Amazon Web Services that says you have to segregate and separate your networks in any particular way. It's all up to you, whatever makes the most sense for your application and for your business. Some businesses choose to segregate their networks by department, whereas finance department has their resources in their VPC, and accounting has their resources in their own VPC, but they're connected and they can talk to each other. Accounting needs access to resources that are in the finance department, so they would peer those two VPCs. In another situation, maybe you need centralized resources where you have various departments. They are all essentially isolated from each other. We don't want these departments really gaining access to each other's resources, but they all need access to the corporate intranet or the corporate file sharing server. Here's that example of you have those kinds of shared resources in one VPC, and you keep your specific departmental resources in their own VPCs. Another approach to VPC peering might be that you put shared resources in a VPC and you have different customers that have access to that. Each customer or each vendor having their own VPC in their own account, and then you're granting them access to your pool of shared resources. So again, it's all arbitrary. Amazon does not dictate how we do this, other than that, as we've talked about, VPC peering is a one-to-one relationship with no overlapping IP ranges. Other than that, you can pretty much do what you want, whatever makes sense for your application and your business. Okay, so now let's take a look at a demo where we peer two VPCs. From our VPC dashboard, I'm going to make sure that we have filtering turned off. I'm going to look at our VPCs, and again, we have the default VPC that just comes with our account. I typically don't use that. And we have the VPC that we've created earlier. For the sake of peering two VPCs, I'm going to create another one, just really quickly. I'm going to call this one Data Services. Typically, one approach that I commonly use is to segment networks by purpose. So I might put certain types of applications in one network and put databases in another. And that way I can control the flow of traffic between the applications and databases. I can allow certain people access to databases via VPN. But of course, that's up to you. How you segment your infrastructure is completely up to you. So we've already used 10.2. Here I'm going to use 10.6. Totally arbitrary. It's up to you. And I'm going to create that. So now, once this creates, you can see we have two VPCs now, one with 10.2 and one with 10.6. And we want to peer these VPCs. We want our web servers that are here in this particular VPC to be able to talk to databases off in another VPC. And we will do that by peering those two. So I'm going to go down to peering connections. You can see that we don't have any peering connections in this region yet. So I'm going to create a VPC peering connection. I'm going to call this one Live Lessons to Data. That's my particular pattern. That's a pattern that works for me. It helps me to know that I'm peering a VPC called AWS Live Lessons to a VPC called Data Services. Whatever you name it is totally up to you. I'm going to choose two VPCs. The first one will be the AWS Live Lessons VPC. Both of these are in my account, and I'm going to choose the other one being the Data Services. Now, it could be another account. That's a really powerful feature within VPC, is that we could have multiple accounts in our organization. We could be dealing with customers or vendors and wanting to peer with their VPCs. I'm going to go ahead and create that VPC peering connection. Just to verify, we're peering 10.2 and 10.6, so the other VPC. I'm going to hit OK. From here, you'll see that this particular peering connection first goes into a pending acceptance state. This is just an extra layer of security that Amazon puts in to ensure that, yes, this is indeed something you want to do. This is especially true for cross-account peering. So I'm going to, from here, click Accept Request. Yes, accept. I do indeed want to peer those two VPCs. You can see here our VPC peering connection has been established, so I can close that. You can see now our peering connection is active. Now we can start routing traffic to those two VPCs. And we do that, again, we need essentially converse routes where the VPCs point towards each other by way of the peering connection. So I'm going to start with 10.2. Let's take our public traffic, and I'm going to add a route to it that says any traffic destined for the other network, 10.6, will be routed through our peering connection. And from here, I'm going to choose that PCX peering connection. I'm going to save that. And so that's only one half of the routing. We need to do the other half in order for traffic to get back. So I'm going to filter by 10.6. And in this case, we only have the default route table, which is OK for now. I'm going to choose that one. In this case, we only have local traffic. I'm going to edit that one and add another route that says traffic destined for 10.2/16 will also go to the peering connection. And from here, I'm going to save that. And now we have these two VPCs peered. We have our peering connection, and we have our routes in place. The only other thing that we would need to do is to edit the network access control list so that certain ports are allowed to flow between those subnets. So that is how we peer multiple VPCs within AWS Virtual Private Cloud. Here we'll talk about VPN access into our Amazon Web Services Virtual Private Cloud. Of course, we have resources within AWS VPC, be it application servers, databases, and so on. And we want to give those, we want to make those accessible to our on-premises network. Or we could say that we want to extend our on-premises network into the cloud or into VPC. And so in order to do that, we need several things. One, we need a virtual gateway that is attached to our VPC, and we need a customer gateway which represents the physical hardware on premises. And we create a customer gateway by just specifying the static public IP of our hardware on the on-premises side. Now, with VPC peering, Amazon won't let you create a VPC peering connection if the IP address ranges overlap. But with VPNs, that's not necessarily the case. Amazon has no way of really knowing what your ranges are on your corporate side. So it's up to us to be aware of IP range overlaps. So by having those overlaps, you can get some weird routing bugs where traffic won't go where you think it's supposed to go. Very much like VPC peering, the VPN access is also one-to-one, no transitive peering and no edge-to-edge routing. And so very much like peering, if we want our on-premises machines to be able to reach resources over here in VPC-C, we need another VPN connection. We cannot use an existing peering in order to get there. So another way to look at this is like this. We have a VPC with the range of 10.2.0.0.16, and we want to give access to our on-premises network at 192.168. So again, we need a virtual gateway that is attached to our VPC. We have our customer gateway, which represents the physical hardware. It could be, a Juniper device, a Palo Alto, a Cisco ASA, whatever it is. This is our hardware on our on-premises side. And then we would establish the VPN connection between those two. So we actually have three resources within AWS that we're managing: the virtual gateway, customer gateway, and then that third being the VPN connection itself, which is a connection between the VGW and the CGW. Now, just because we have those things in place, just because we have those three resources in place, doesn't mean that traffic will flow. Remember that we also have to have routes. Routes are the way in which we control the flow of traffic. And so here on our VPC, we're going to create a route table that says traffic destined to our corporate range, our VPN range of 192.168/16, will be routed to our virtual gateway. And of course, on the customer side, whatever device you're using would also require its routing rules to say that range of 10.2.0.0.16 needs to be routed over the VPN. Very much like VPC peering, we could route the entire VPC to our VPN, or we could route just specific subnets. We could apply this route table to one or both of the subnets here in our VPC. On our customer side, we could choose to route, again, the entire network or just a subset, one particular subnet. All right, now let's talk about AWS Direct Connect. Direct Connect is a way of getting direct access into an AWS region over private networking. In many situations, we have the need for on-premises applications or data to get to and from Amazon Web Services region without going over the open internet. Maybe we need greater bandwidth and better performance, and we can get that with the Direct Connect. Direct Connect comes in two options, being a 1 gig or a 10 gigabit per second connection. We can have one Direct Connect connection terminate into one or multiple VPCs. Now, in order to establish this connection, we would provide our LOA CFA to whatever vendor is local to us. In many cases, that might be AT&T, Level 3, Equinix, the list goes on. There's a number of providers. It just depends on where you are in the country or around the world. Another great benefit, besides the increased bandwidth, the consistent network performance, is that we should keep in mind that data transfer out of AWS, whether it's data leaving a load balancer, it's data leaving simple storage service, or leaving DynamoDB, we pay for all outgoing bandwidth. And so if we have bandwidth coming out of S3 and going back to our corporate network or our co-location facility, we could see a lower data transfer rate by using Direct Connect. So in this example, we're seeing our corporate data center. This could be our on-premises network at our headquarters. This could be our data center or a co-location. And we have a Direct Connect. In this particular Direct Connect, we would divide into multiple VLANs where each VLAN terminates into a separate virtual gateway attached to a VPC. So we're leveraging one Direct Connect to gain access to multiple VPCs. So again, Direct Connect is a really great way to achieve a private dedicated connection directly into an AWS region. Applications need compute power, and AWS offers an extensive collection of options geared toward every possible use case, from simple low-traffic websites to APIs handling billions of events to genomic sequencing, scientific computing, and real-time data processing. In this lesson, we will cover the compute options offered by Amazon Elastic Compute Cloud, serverless computing, along with a couple of great demos. Let's talk about Amazon Elastic Compute Cloud, or EC2. With Amazon Elastic Compute Cloud, what we get are virtual machines, and we call them instances. So one virtual machine would be an instance of EC2. These are based on the Xen hypervisor, and they come with sort of a price-fixed menu, you could say, of CPU, memory, disk, and network I/O. We don't really get to control CPU and memory and disk or network I/O like individually. But Amazon has done a really good job of creating a collection of machines, various types of EC2 instances for different types of workloads. And they come with various degrees of CPU, memory, disk, and of course network I/O. With EC2, we can launch from one EC2 instance to thousands of instances if we need to. Now, it's important to understand that there are service limits. Typically, from the start, your account is initially limited to a certain number of instances depending on the instance type. That's considered a soft limit, meaning that you can submit a support ticket request to lift that limit. They put that in place just as a way to limit resource consumption in the case where people might have runaway scripts or maybe they aren't paying attention to what they're doing. So with EC2 instances, we have a very powerful range of compute options for various types of workloads. It's important to understand that this is a very different paradigm than what we might be used to. In traditional IT, where we had long-living servers that we assumed would be there for years on end in a rack somewhere, that is not the case anymore. We're getting away from that paradigm, and we're assuming a paradigm where our EC2 instances are disposable, where if there's something wrong with it, we throw it away and start anew. And we have systems that we'll talk about later that can help that machine bootstrap and configure, and so to have it right back up and running where it should be simply by throwing it away and recreating it. Let's talk about the Amazon machine image. So an Amazon machine image is where all EC2 instances start. An Amazon machine image is essentially a bit-for-bit copy of the root volume. In this particular example, the root volume could be an EBS volume, an Elastic Block Store volume, or it could be an instance store, and we're going to talk about what exactly that means coming up. But on that root device, we have our operating system, we have whatever applications were installed, we have users and groups, and we have however things are configured, so on and so forth. If we then create an image from that, that bit-for-bit copy will contain the operating system, the applications, and all the configurations. From there, these Amazon machine images are stored in S3, but they're stored in sort of like this admin zone that we don't have direct access to. We don't really have direct access to the raw data that makes up the Amazon machine image, but we do know that those machine images are stored in S3, and we'll talk more about why that's important later when we cover storage. From that image, that will allow us to launch clones of the original machine. So if we install, let's say we install Linux and Apache and our application on this machine, and then we want to clone that, we would first create the machine image and then use that image to launch an exact copy of that machine over and over again. We could launch one clone, we could launch 1,000 clones. That would be up to us. But whatever machines are launched from that machine image will all come out exactly the same. So again, Amazon machine images are where all EC2 instances start. They are a bit-for-bit copy of the root volume, and when you clone those machines, they will all have the same OS, the same applications installed, and will all be configured in the same way. Okay, so now let's run through a demo of launching a Linux instance in Amazon EC2. Okay, so you can see we're already logged into the AWS console. We're on the initial dashboard, and from here I'm just going to go to EC2. It's important to make sure that you're in the right region. Here we're using the US East 2 Ohio region. I can change that from here. Again, as we've talked about, whatever region you operate in is really according to the needs of your business. Are you trying to serve end users in a particular area? Are you trying to meet some kind of data compliance regulations? Or are you just simply trying to get the lowest cost? Whatever that answer is will determine what region you choose. For the sake of this demo, doesn't really matter, but US East is one of the newer regions, so I just want to try it out. I've seen this happen to folks where you launch machines and you launch different resources, and then you come back later and go, wait, where are they? And it's simply because you inadvertently switched to a different region. So if that happens to you, if you can't find your resources, just make sure that you have the right region selected. So from here in the Ohio region, you can see that we don't have any instances running. So in order to launch one, I'm going to go down here to AMIs. Remember what we talked about, that all EC2 instances start with the Amazon machine image. So I'm going to click on that. And you can see that I have this filtered by, I'm going to change this real quick to show you, images owned by me. I don't have any yet. I'm going to change this to public images. And these are all of the images that have been made public by various publishers, namely being Amazon Web Services. Other folks like Canonical publishes Ubuntu, Red Hat publishes a number of things like, of course, Red Hat Enterprise Linux, CentOS, Fedora. There's others like Zend and Viata. All kinds of public images are available here. So for the sake of this demo, I want to launch an Amazon Linux-based machine. So you can see when I click here into the filter, I get a number of attributes by which I can filter our images on. So the first thing that I want to do is filter by, I know that this is Amazon Linux, so I'm going to change the owner to Amazon Images. And now I can see that all of these images were published by Amazon Web Services. I'm going to also change the platform to Amazon Linux. I'm going to make sure that the architecture is 64-bit. And from there, you can see, if we were to scroll through here, we could see that the list did get shorter. It's hard to see that, but we have narrowed it down, and this is the one that I want. I want x86 64. The EBS that we see here means that the root volume is based on an elastic block store volume, and we'll talk more about that later. So now that I have the AMI that I want, I'm going to go ahead and hit launch. From here, you can see we can choose from various types of machine sizes. We have different families, such as the T2 family, which is really great for development, testing environments, experiments. It's potentially good for low traffic applications in production as well. We have the M series, which is a mixed use. They give us a good balance of CPU, here 2 cores and 8 gigs of RAM for the M4.large. If we compare that to the C4 large, you can see that we have 2 cores, but we have half the memory. So the C4 is what we consider a compute optimized instance. It has less memory, but essentially more compute power. We get into the R series, and that's going to give us much more memory. These are memory optimized. We get into some really large storage capacity. These are high performance computing. We can even get into the GPUs, and so on and so forth. For now, for the point of this, we don't really need a whole lot. In fact, the T2 Micro is free tier eligible. You can see that certain instances like this one here, Amazon Web Services will give us the first 12 months of this particular machine for free. That is the first 12 months following your AWS sign-up date. My particular account is too old for that. I don't qualify for the free tier, but for those of you following this course, you probably will. So using the free tier services, a number of services come with a free tier. It's a really great way to get into Amazon Web Services and try things out and get to know these services without spending any money. So I'm going to go ahead and choose the T2 Micro. I'm going to click Next. And from here, we can say I want to launch one. Maybe I want to launch 10 machines. We can change that if I wanted to. For the sake of this demo, we're just going to launch one. Here, we'll talk about spot instances later on. We might want to choose this if we want to get a lower price, and we'll save that for later. Here, we can choose the network. Here are the networks that we created earlier. For the sake of this demo, I'm going to launch this into 10.2. And because I don't have a VPN established right now, I need these machines to be publicly available. So I'm going to choose one of our public subnets that we created. I'm also going to make sure that the auto-assigned public IP is using the subnet setting that we turned on, so that yes, these machines will automatically get a public IP. You can recall that we talked about roles. I'm going to choose the My Application role that we created so that later, if I want this particular instance to have the ability to communicate with other AWS services on my behalf, then it already has a role and I can just go in and add permissions to that role. It's important to know that you have to add the role at the time you launch the machine. If you launch a machine without a role, it's too late. You'll have to terminate that machine and start over. From here, you can see that we do have some control over our network interfaces. We could add more if we wanted to. There are some advanced options down here, such as UserData, that we'll talk about later. I'm going to click Add Storage, and from here, you can see that our root volume is an 8 gig volume. It's just a simple magnetic volume, and it will be hosted by the Elastic Block Store service that we'll talk about later. Now, if I wanted it to be faster, I might want to choose a general purpose SSD or a provisioned IOPS SSD. Again, we'll talk more about those later on. For the sake of this demo, magnetic is perfectly fine. I'm going to click Next and add some tags to my instance. Tagging is a really great way to keep your environment organized. So as you get further into Amazon Web Services, as you start to deploy applications and services, you'll end up perhaps with dozens or hundreds of EC2 instances, security groups, VPCs. It's really important to be able to tag these resources in a consistent way, in a predictable way, so that you can come back and filter and find particular servers for particular needs. So in this case, I'm going to name this one Linux Demo. I might also want to create other tags, such as the environment that this machine belongs into. The environment might be dev, stage, production, and so on. I might also add an application tag and call this one demo. So tags are up to you. They're pretty much arbitrary, but again, I would highly recommend that you leverage these as a way to keep your infrastructures organized. From here, I'm going to leverage the security group. I'm going to select an existing one because we already created one. I'm going to use the web server that we created. You can see here that we have our port 80 and 443 is open from the internet. I'm going to go ahead and click Review and Launch. And it's just telling me, you know what, port 22, you don't have access to that, so we're going to fix that here in just a minute. It's also saying, it's somewhat warning us that we are continuing with the magnetic drive, and it's telling us that general purpose SSD volumes will be faster. And it's giving us the choice to make our boot volume general purpose for all instances going forward, or just for this one, or we could just continue with magnetic. So perhaps I'm just going to say, you know what, general purpose SSD is probably better. Let's go ahead and stick with that for all things moving forward. That'll be up to you, whatever makes the most sense for your business. So now we get an opportunity to review this instance. I'm going to just scan through here and make sure, yes, we're using an Amazon Linux AMI. We're running on a T2 micro. We have the right security group attached with the right rules in place. Just take a quick look at the storage. We don't really need any more than 8 gigs, so that's going to be okay. Make sure that we have the right tags in place. We have our name, our environment, our application. And I'm going to go ahead and click Launch. Now, key pairs are necessary for logging in to the operating system of this particular machine. So I don't have an existing key pair. You can see that I don't have any yet, so I need to create one. I'm going to say create a new key pair. I'm going to call this one AWS Live Lessons, so I can use this for other things. Now, at this point, if I don't download the key pair at this point, then I will never be able to get it. Amazon Web Services only gives us this one opportunity to download the private half of that key pair. From that point, that private key is not kept by AWS. And so if we don't download it here, we'll have to go back and create a new key pair. If you lose the private half of that key pair, you won't be able to get into your instance unless you have already configured your instance to allow login without private keys. So I'm going to go ahead and download this key pair. You can see there it is. We have a .pym file that we're going to modify here in just a minute. Now that we have the key pair created and selected, I'm going to hit Launch Instances. There you go. Now you can see that our instance has launched, and I can click here. This is the ID of the instance. I'm going to click that, and it will take us to the instances dashboard where we can see that our T2 Micro is now running in US East 2A availability zone. From here, we can see that we have a public IP that was automatically granted to it. We can see that we also have a private IP in the 10.2 range. So from here, what I'm going to do, what I need to do is make sure that this particular machine can be reachable over port 22. So really quickly, what I want to do is create a new security group. I'm going to call this one SSH. Make sure that it belongs to the right VPC. I'm going to add SSH from my IP, and it will select, you can see here that it selected the right IP that I'm currently coming from. And I'm going to go ahead and create, I need a description. And then I'm going to create that. Now that we have our SSH security group, I'm going to click this tag here and make sure that that also has that name. I'm going to come back to our instance. I'm going to make sure that we have that instance highlighted. I'm going to go to Networking, change Security Groups, and choose the SSH security group. Now that we have that, you can see here are our security groups. I'm going to click those View Rules and make sure that port 22 is open, port 80 and 443 are open. So from here, I'm going to copy this public IP address. I'm going to make sure that I have access to that PIM file that we downloaded. There we go. Now I'm going to SSH using that key. All right, so now that we have our key downloaded, I want to shell into that instance. I want to make sure that I have the appropriate permissions on that key. So I'm going to change those to 400. And now that the key has the right permissions, I'm going to use that. And I'm going to log in. In the case of Amazon Linux, the super user is ec2-user at there's the public IP of our instance. And there we go. Now we've logged in. You can see we have a shell into our T2 Micro running Amazon Linux. And that's it for launching a Linux instance on Amazon EC2. Now let's talk about key pairs within Amazon EC2. Key pairs, or public-private keys, are the way in which we can authenticate into the operating system of our EC2 instances. You remember when we talked earlier about authenticating against the AWS API, we use a certain set of access keys for that using IAM users and groups. What we're talking about here is the OS level of authentication. So here, in order to get into the operating system or EC2 instance, we need a key pair. Now, these are 2048-bit SSH2 RSA key pairs. We will create these within the AWS console, and then when we go to launch an EC2 instance, we will choose that key pair at that time. Now, when we create the key pair, Amazon Web Services will keep the public key. They will give us the opportunity to download the private key, and then at that point, they will no longer keep the private key. So you do have one short window in which to download the private key before Amazon gets rid of it. How this works is that when we launch a Linux EC2 instance, Amazon Web Services will take that public key that they're keeping and they will add it to the .ssh authorized keys files for your particular admin user. Like in the case of Ubuntu, they will add it to the Ubuntu user. In the case of Amazon Linux, they will add it to the what we call the EC2 user. And we will use it when we go to log in or SSH into that Linux machine. We will use our private key that we downloaded in order to authenticate against that operating system. In the case of Windows, the administrator password will be encrypted using the public key, and we will use our private key to decrypt the Windows administrator password. So again, key pairs are the way in which we authenticate into the operating system of Amazon Elastic Compute Cloud instances. Here we're going to talk about the instance metadata service within Amazon EC2. Now, the instance metadata service is a service by which we can retrieve information about an EC2 instance. You'll notice this very unique IP address here, 169.254.169.254/latest/meta-data. From that URL, if we were to log into an EC2 instance and visit that URL, we could do it in the case of Linux, we could use curl. In the case of Windows, we could use PowerShell commands to retrieve information from that URL. It's important to note that this particular service is not available outside of EC2. It's available within an instance for the instance to get information about itself. We cannot use this service to get information about another instance, but only for one instance to get information about itself. And from that service, we can retrieve such things as the AMI ID that the instance is using, the host name, the instance ID, the type of instance that it is, the private IP address, so on and so forth. There's all kinds of information we can use or get from the instance metadata service. And typically, we will use this service with scripts so that we can bootstrap this instance and get it up and running, configured automatically. So the instance metadata service is often used with bootstrapping scripts so that when the instance boots, those initial scripts can call the instance metadata service, get information about the instance, what its host name is, what its ID, and use that information to automatically configure and bootstrap this instance to install software, to configure software, and to get that instance into a state where it can start doing its job automatically. So the instance metadata service, again, is available at this URL, only available from within an EC2 instance in order to help bootstrap and configure that server in an automated way. All right, so now let's run through a demo of the instance metadata service in Amazon EC2. I'm going to, from my terminal, I'm going to SSH back into a machine that we created earlier. Now that I've got a shell into my EC2 instance, we can see here I'm going to just run curl against the instance metadata IP address, which is 169.254.169.254/latest/meta-data. And what I get is a menu of all of the things that are available from that particular service. So you can see here, starting at the top, if I want to get the AMI ID of the machine that's running, I can replay that and just type AMI-ID, and there you go. You can see that it gives this to us there. If we wanted to script that, let's actually try one of the other ones. Like the instance ID is actually one that's generally most useful for doing automated scripting types of things. So let's try that again and use the instance ID. And there we go. You can see it gives us back the instance ID. And this is how we might actually leverage that. We could say something like export instance ID equals, I'm going to copy this, put that in $ parentheses, hit return, and now if I say echo $instance ID, there we go. Now we have that instance ID listed or exported to an environment variable. From there, we could have different types of shell scripts leverage those environment variables for bootstrapping this instance and getting it up and running. Perhaps this instance needs to grab its instance ID and report back to some kind of configuration management tool or some kind of monitoring tool like Nagios or the like. We could also do the very same thing and use its local IPv4. Let's do that. Let's grab the local private IP address. Local-IPv4. And there you go, there's the private IP address of this particular instance. So you can see the instance metadata service is a really powerful way for our instances to get information about themselves. Again, I can't reach this IP from anywhere outside of EC2, and I cannot use this IP to get information about another instance. It's for an instance to get information about itself, and it's a really helpful tool to use for auto configuration. It will help us maintain high availability. It'll help us create environments that are self-healing and automated. So that is the instance metadata service in Amazon EC2. Let's talk about bootstrapping with what we call UserData in Amazon EC2. UserData is ultimately a script that allows an EC2 instance to automatically configure itself on first boot. So this is one of the keys, along with using multiple availability zones. This is one of the keys to high availability and what we call self-healing infrastructures. I personally don't really like being woken up at 2 o'clock in the morning because Apache crashed or a server failed and I don't really want to have to get up in the middle of the night and reinstall and reconfigure software. Ultimately, I want my environment to automatically handle that stuff for me. Bootstrapping with UserData is one of the ways that we can do that. Now, again, this is executed only on the first launch. What happens is that this script, on that first boot, it will be ran and then it will be locked via a lock file so that it doesn't happen if you reboot. In the case of Linux, if the very first line of your user data is something like #bang/bin/bash, then that will execute that script using the bash binary executable. Otherwise, you can use any executable software that you have installed that is a part of that Amazon machine image when the instance boots. You could use Node, Python, Go, Ruby, the list goes on. In the case of Windows, we have the option of having that be a batch or a PowerShell script. If you leave the top line blank, then the user data would just be a list of environment variables that a script that's already a part of the machine image could then pick up and start using. So again, bootstrapping with user data is a really important key to maintaining a highly available and self-healing environment where our EC2 instances can use this script to configure themselves on first boot. Now let's run through a demo of launching a Windows instance on Amazon EC2. You can see we're logged into the AWS console. Again, we're in the Ohio region. We can see that we have one running instance, our Linux instance that we launched already. And from here, we're going to go ahead and launch a Windows instance. Again, EC2 instances start with the AMI. So I'm going to click over here. And I've already done some research just to save a little bit of time and found the Windows AMI that I want, which is this one here. So if you know the ID, you can just paste it there. And this one is going to be Windows Server 2012 R2, English, 64-bit. So I'm going to click that. I'm going to pull this up. You can see some more details around that at the bottom. So I'm going to go ahead and click Launch. The T2 Micro, again, is free tier eligible, so in the cases where you're just wanting to experiment or check things out, be sure that you make use of that free tier. So I'm going to go ahead and click Next and configure the instance details. Again, in this particular case, we only need one, but we could launch more of it if we really wanted to. I'm going to make sure that I'm in the appropriate VPC, 10.2. I'm also going to choose a public subnet. Either one of these would suffice. I'm going to go ahead and choose, in this case, public B. I'm going to ensure that I'm getting an auto-assigned public IP. I'm going to make sure that I have the IAM role attached so that later I can make use of that if I need to. I'm going to scroll down here just to remind you that such things as user data and other things are found here for when you go to work with that. I'm going to take a look at storage. You can see here that Windows needs a bit more space than Linux, so these machines default to a 30 gig volume. In this case, it's defaulting to general purpose SSD. So our root volume will be based on an elastic block store, which is separate from the machine, and we'll talk more about the details of that service later on. You can also see that this particular volume has the flag delete on termination enabled so that when we terminate this instance, this particular volume will also be terminated. But that's optional. You can uncheck that if you want the root volume to stick around after the instance is terminated. We're going to tag instance. Again, I'm going to call this one the Windows server. Perhaps give it an environment tag. Again, be sure to leverage tagging. Really great way to organize your infrastructure. There is also a way, if you leverage what's called detailed billing. Detailed billing can send logs every 6 hours or so. it can send logs to an S3 bucket, and your billing can be broken down by tags. So that if you're leveraging tags consistently, you can see exactly what you're paying for across different environments, across different business units, across different applications, and so on. And so I'm going to call this one dev. You can see that this comes up because I've used that before. Let's configure the security group. I'm going to select an existing group, the web server. So in case I wanted to run IIS here or something else that's running on port 80 or 443, and I also want to, in this case, I've already gone and made a change to the SSH security group that also allows port 3389 for RDP. So I'm going to review and launch. Make sure that we're running a T2 micro. We have the right security groups. Yes, RDP is open on that one. We have the right size volume, and we have the right tags in place. I'm going to go ahead and launch that. Here, since we've already created a key pair, now remember, key pairs are necessary in order to be able to actually authenticate into the operating system of your machine. So I'm going to acknowledge, yes, I have this key, and I'm going to launch that instance. So from here, I can click this ID and see that my Windows server is in a pending state, and it will be there for however long it takes that machine to boot. Linux instances typically boot much faster, but the Windows server here is going to take a few minutes. Okay, so now you can see that our machine has changed into a running state. So one thing to note is that so long as your machine is in a state ending in ing, such as running, pending, terminating, stopping, any of those types of states, you will be paying the hourly cost of that machine if you're using the on-demand billing model or the spot billing model. As soon as the machine goes into a stopped state or a terminated state, that's when you stop paying. So from here, again, I'm going to take this public IP address. I'm going to copy that. I'm going to switch over into the remote desktop. Going to create a new connection here. The name would be administrator. Now the password we need to get here from the AWS console. I'm going to say get Windows password. And now you'll see here, in order to get that administrator password, it was encrypted using the public half of our key pair. You can see the public half of the live lessons key. Amazon does not keep the private half. And so in order to decrypt this password, we need to paste the private half in there. So here, what I'm going to do is I'm going to echo that out in a way that will let me copy that. I'm going to pipe that to PB copy. So now it's copied to my pasteboard, and from here I can paste that private key into that window, and now I can decrypt the Windows password. And so you can see here, again, here's my public IP. Username is administrator, and my password, I'm going to copy that, paste that there. And then I'm going to double click on that. It says the certificate cannot be verified. That's okay. I understand that. I'm going to just say continue. And sometimes it takes a minute for that to come up. And there we go. Now we have an RDP session into our Windows server running on EC2. And there we are. Now we're at the desktop of our Windows Server 2012 R2 From here, we can go about our business, do what we need to do to get this machine configured. If we want to install any applications, if we want to add users, configure this particular system however it's meant to be run. And from there, we would want to be sure to create an Amazon machine image from it so that we could clone this if we needed to. In the case of systems that are meant to be distributed, it would be important that we create a machine image that would allow these systems to scale very quickly. Again, it's important to think of these systems as being automated. We don't want to have to log in and do things manually every time. We want them to be automated. So from here, again, I can go to the Start menu and do whatever I need to do. From here, I'm just going to go ahead and log out, and that will be our demo of launching a Windows instance on Amazon EC2. Now let's run through a demo of stopping and terminating instances in Amazon EC2. So again, we're back at the AWS EC2 dashboard. You can see we have two running instances, the Linux instance and the Windows instance that we launched earlier. Now, it's important to note that the root volume, I'm going to show you here, the root device is, if we click this, you can see that the root device is an EBS volume. That means that the operating system is booting from a volume that is hosted by the Elastic Block Store service, so that the Elastic Block Store is a device that is apart from the machine itself. So because of that, and we'll talk more about the details of EBS later on, because of that, that allows us to stop the instance rather than just terminate it. So if we want to stop the instance and sort of keep it around but not actually use the CPU and not be billed for it, then we can potentially stop these machines and then come back and start them again later. So in the case of Windows, I'm just going to go ahead and show you that from here, I'm going to highlight just this one. I'm going to go to Actions, Instant State, and you can see I have the ability to stop that machine. Again, stopping and terminating are two different things. Terminating means that it's gone for good. Stop just means that we will stop paying the hourly cost of the machine, and then we can restart it later. So I'm going to go ahead and click Stop. And we're going to talk about this particular point more later on, but for now, we should know that if there are any data on the ephemeral storage of that device, it's going to be lost. And we'll, again, cover ephemeral storage later on. So I'm going to stop that machine, and you can see it's in a stopping state. We're still paying the hourly cost so long as it's in a stopping state, but as soon as it becomes stopped, then that's when we stop paying the hourly fee. While that one is running, I'm going to go ahead and click our Linux instance. I'm going to go Instant State, Terminate. Oh, whoops, I had the other one selected. Let's make sure that we uncheck that one. You can see now our Windows instance is in a stopped state. So it's still there, it still exists in some way, but it's not actually running. So from here, I could either restart it or terminate it. I'm going to select our Linux instance, come down here, Instance, Terminate. And yes, you can see here, the EBS volume will be deleted when the instance is terminated. And in this particular case, that's what I want to do. I'm going to click Terminate. You can see it goes through a shutting down state, and then it'll go into a terminated state. While that one is doing that, I'm going to go back to our Windows machine and say Actions, Instant State, Start, and I can restart that machine. And now it goes back to a pending state, and it'll take it a few minutes before it goes back to a running state. Sometimes this view might get stuck. We can always hit the refresh button up here, and there we go. Now we can see that our Windows machine is running again, but our Linux machine is now terminated, and we don't have the option to do anything with it. It's completely gone at that point. So that is stopping and terminating instances in Amazon EC2. Okay, so now let's talk about billing options within Amazon EC2. You can see here that we have a number of different billing options we can choose from. We have our on-demand, which is what we could describe as the MSRP. If Amazon Web Services says that a particular EC2 instance costs, let's say, 0.05 cents an hour, then that's what we'll pay. And in that model, we have no commitment whatsoever. If we want a machine for 1 hour, we run it for an hour, we pay for an hour. If we need it for 2 days, we pay for 2 days. So we get what we need and we pay for what we use. Now, with on-demand billing, the availability is not necessarily guaranteed. Amazon Web Services has an unbelievable amount of compute capacity. But there are some times, depending on what other customers are doing at that particular time, you may see, and in the 7 years that I've used Amazon Web Services, I've only seen this happen maybe 3 times, where when you go to launch a particular size EC2 instance, it might come back and say, we're out of capacity for that size machine. Again, that's fairly rare, but it is possible. So the availability or the capacity reservation is not necessarily guaranteed. With reserved instances, you do have that option. The Amazon Web Services recently made a change to the reserved instances model where you have the option to reserve capacity or not. Now, for applications that are long-living, like web servers, application servers, databases, applications that need to meet demand all the time, you can save a significant amount of money over the course of a year or 3 years, depending on the term you're willing to commit to. We have these choices, either a 1 or a 3-year term. And you can save a very significant amount of money over that by using the reserved instance billing model. Now, you'll see here that with the reserved instance billing model, you have a choice of paying a certain amount up front. You can pay a no upfront fee, you could pay a partial upfront or everything upfront, the entire year's cost or the entire 3 years cost upfront, and get the most discount. Then, of course, we have what we call the spot market, and that's based on supply and demand, and we're going to talk about that here in just a minute. So these are the 3 main billing models that we have to choose from: the on-demand or the MSRP, reserved instances, and spot instances. So let's take a look at more detail around the reserved instance and spot instance pricing. Again, with reserved instances, we're going to make some kind of an upfront payment. And now we do have a choice to make no upfront payment, but it's important to know that regardless of what we pay up front, we will pay the hourly fee regardless of use. So if we choose to make no or a partial upfront payment, then we're essentially committing to paying the hourly fee for every hour of every day throughout that 1 or 3-year term. Now, again, guaranteed availability is an option that we can choose from, so that means that even if we aren't running a machine, Amazon Web Services is reserving one for us if we choose that option. And again, very significant savings over the on-demand price. And so for constant applications, for databases, for things that just need to be there all the time, or at least for things that need to be there a great majority of the month, the reserved instance model is the best way to save money. Now, the spot instances, again, this is based on supply and demand. What this means is again, Amazon Web Services has a vast amount of compute capacity. Depending on the level of usage within a particular availability zone, let's just take one particular size instance. Let's say the M4.large machine size. If there's a large amount of capacity for that machine size, but no one is using it, then Amazon Web Services will offer that machine in the spot, what we call the spot market, at a reduced rate, a very, very reduced rate. And the hourly fee could be a mere fraction of the on-demand price. And so what we do, if we want to leverage the spot market and get a lower price, when we launch that EC2 instance, At the time we launch it, we will specify the maximum amount of money that we're willing to spend on that particular instance. And then as long as the current market rate for that particular size machine is lower than our maximum, we will get that instance and continue to run. It's important to know that if the market price, again, according to supply and demand, if the market price rises above our maximum spend, then the instance can be terminated by AWS. Now, in those cases, we do get a warning. We get a 2-minute warning that can be a notification that can be delivered to that machine to tell our application to stop what it's doing, save its work, and prepare to be shut down. The spot instances are a really great way to save money for things like batch processing, for if you want to just run a simple test or an experiment on something, if you're wanting to do certain type of reports that are essentially things that are happening fairly infrequently. You know that the job is going to take a short period of time, and it's important, as I mentioned, it's important that your applications tolerate interruption. So for batch processing, as an example, you might do a short job, check, save what you're doing, record a stopping point so that in case that instance was terminated and it comes back later, you can pick up where you left off. So these are our billing options. We have on-demand, which is the MSRP. You pay what Amazon says the price of the machine is going to be. We have the reserved instance model, which is really great for long-running applications, which comes in a 1 or a 3-year term. And then, of course, we have the spot market, the spot instances, which are based on supply and demand and are really great for short-running, temporary kinds of jobs. All right, so now let's review a use case of a highly available web application in Amazon EC2. Let's start with our VPC. You'll notice here we are leveraging all 3 availability zones in the US West 2 region. Again, by leveraging every availability zone, we can help maintain high availability and fault tolerance. Across that region, we have a VPC. Our VPC would have an internet gateway attached here so that our subnets can communicate with the internet. We would also have a customer gateway and a virtual gateway and a VPN connection back here so that our on-premises can communicate with our VPC as well, and database administrators or developers can get in and access the database. You'll notice that we have various subnets essentially within Amazon Web Services. For a 3-tier application like this, it's recommended to use a subnet per tier per availability zone. So you'll notice in a classic 3-tier application, we have our public subnets up here where we put our elastic load balancer. We'll talk more about the details of that service later on, but for now, suffice it to say that behind the scenes, the load balancer itself has nodes that need a place in the network. And so we're going to specify these /24 subnets for our load balancer. That /24 subnet will give us somewhere around 250 available IP addresses. So across the 3 of those, that's somewhere around 750 possible nodes. That's plenty of room for our load balancer to expand and spread out and scale as our traffic increases. And the same thing is true back here for our application servers. So we have yet another tier. So we have subnets for that tier, 1 per availability zone. Again, these are /24s, giving us plenty of room to scale horizontally. So again, this is key to high availability and fault tolerance. If one of these machines were to fail, then we still have another 2 behind the load balancer. Traffic is being distributed among those other machines in the background. So if this entire availability zone were to fail, which is very unlikely, but still possible, If that availability zone were to go down, again, we still have another 2. So this is very key to high availability and fault tolerance. And back here on our database tier, again, we have subnets per tier per availability zone. Now you'll notice here that we used a smaller range. We used a /28 because we probably won't scale our database as a relational database system. While we can do read replicas very easily, a lot of relational databases aren't necessarily designed to scale horizontally without sharding and a lot of complex stuff. So we don't expect that our relational database will expand horizontally very far. So a /28 is the smallest range that we can use within Amazon VPC, and that's plenty of room for our databases. So this is classic 3-tier architecture, classic highly available web applications within Amazon EC2, where we have a load balancer up front in a public subnet, our application servers in private subnets, databases also in their own private subnets, so leveraging VPN access, and of course our public subnets leveraging an internet gateway. One of the fundamental architectural questions that we're always asking is what happens when this fails? And again, just to review that one more time, what happens when one of our application servers fails? Well, we have another 2 still running, able to handle the traffic that is not being served by the one that failed. What happens when a data center becomes unavailable? Well, we still have another 2. We have another 2 availability zones. Think about that for 1 minute. Coming from traditional IT, coming from a place where you were perhaps running your own data center or co-location facilities, the ability to be resilient to the loss of a data center in traditional IT was very expensive and very complex. It not only did it cost money to either build or lease that center, but it also cost a lot of money to hire a team of people to maintain it. Here, within Amazon Web Services, the ability to leverage multiple data centers is literally at the click of a button. And the only thing that it costs is the price of the machines that you have in there. The actual ability to leverage those additional data centers is essentially free. It's just included in the price of the machine. And that's a very different paradigm from where we may be coming from. So again, this is classic 3-tier architecture in Amazon EC2. All right, so now let's talk about AWS Lambda. AWS Lambda is what we might describe as serverless infrastructure. Serverless meaning that we don't need to launch EC2 instances and deploy code in order to get our functions to be executed. All we have to do is upload or create our functions directly in Lambda, either via the inline editor or uploading a zip file containing all of our code. And the AWS Lambda service just handles it for us. Again, we don't have any servers to maintain or manage or launch or even think about. We just simply give our code to Lambda and it does it for us. Now, how we pay for this is per 100 milliseconds. So every time our code runs, for every 100 milliseconds that our code is executing, we pay some particular fee. Now, once we have a function within Lambda, we can invoke that function either manually, directly. We could just say, hey, run this. We could use the API, the Amazon CLI tools, the command line interface, or we can register other types of events within Amazon Web Services and have those events trigger a Lambda function. Some of those events might be from CloudWatch. Some of those events might be from the Amazon Simple Storage service. And we'll talk about those services as we go through this course. So again, AWS Lambda is a really great way to just get code running within Amazon Web Services without having to worry about the underlying infrastructure. Here we'll run through a demo of just a simple Hello World application in AWS Lambda. So we're logged into the AWS console. I have gone from here, I've gone to Compute, AWS Lambda, and we find ourselves here at the Lambda initial screen. You can see, we see this because we don't have any Lambda functions saved yet. So I'm going to go ahead and click Get Started. And from here, Lambda gives us a number of blueprints for different kinds of functions. You can see we can start with a blank one. We have some blueprints for processing DynamoDB tables, for getting objects from S3. You can see that AWS Lambda supports various languages like Python, Node.js, and Java. So in this example, we're going to just go with a blank function and use Node.js. So I'm going to click a blank function. And just for the sake of this demo, I don't want any triggers yet. So I'm going to go Next. I'm going to name this Lambda Demo. Just give it a simple description. I'm going to make sure that I choose the Node.js 4.3 runtime. And from here, we have the choice of either editing code inline, or we can upload a zip file or pull one out of S3. So for the sake of this demo, I'm just going to go ahead and edit the code here inline. From here, you can see that we have a simple function called exports.handler. This is how we communicate back to the Lambda service that this is the name of our function that we want to execute. So here, for those of us that might not be familiar with JavaScript, we have a function declaration, which is assigned back to this particular variable. So from here, I'm just going to say console.log and I'm going to output the event variable that we're capturing here so that we can see whatever data goes in will come out here. I'm going to go ahead and scroll down here and say, yes, our handler is the .handler function. Now, in order for the Lambda service to be executed, we need a role. I'm going to go ahead and hit Create New Role from Template. I'm going to say, also call this one Lambda Demo Role. Policy Template. I'm going to choose Simple Microservice Permissions. I don't need a whole lot of memory. This particular demo doesn't require a whole lot, probably even less than that, but you can see that we can go up to quite a bit of memory, 1.5 gigs if we really need to. I'm going to choose that. We could give this a longer timeout if we wanted to. I think probably 30 seconds would suffice. 10 seconds would actually suffice. We don't need access to a VPC, but Lambda does give us that option. If we want Lambda to communicate to services running in a VPC, we could select one here if we wanted to, but we don't for this demo. I'm going to go ahead and hit Next. Review all of that. It all looks good. I'm going to go ahead and hit Create Function. And there we go. Now we have our function. I can come back here to the configuration and change those things if I need to. In the Code tab, we can modify our code if we wanted. I'm going to come up here and configure a test event. And you can see we have a key value pair JSON object. I'm going to get rid of some of these things here, and you'll see that it's yelling at us about our syntax, but as soon as we fix it, there we go. I'm going to change this key to message. I'm going to say hello world. And down here, I'm going to go ahead and hit save, and that will be what we just edited. That object will be given to this function at the time we invoke or execute this function. That object we just edited will be passed in and captured as the event variable, and then we're going to console log that here. So I'm going to go ahead and hit test. And you can see that the output of the function, the very last thing was said hello Lambda. And if we look at the log output, we can see here that this was our message in the code, initial execution, and then the object that was passed in. What I'm going to do is I'm going to change this a little bit. Now the callback, this particular function you can see is also passed in. The callback is how, when we execute that, that's how we inform the Lambda service that our code, that our function is finished. And we're saying we're calling an asynchronous function so that we can wrap things up. So here I'm going to, instead of hard coding a message, I'm going to leverage the message that is passed in by the event. So I'm going to say callback null, meaning no errors were given, and we're going to say event.message. I'm going to say, let's save and test this at the same time. And there we go. Now our message that we added to the event.message object is output here as a result of the callback. And if we go to the logs, we can see that we also got our console log out there again as well. We can also see that it took 197 milliseconds to run that, and we were billed for 200 milliseconds. We only used 8 megs of memory. So that is a hello world example of AWS Lambda, serverless infrastructure. There were no EC2 instances to maintain or create or worry about. We just uploaded a function and the AWS Lambda service handled it for us. All right, so let's run through a use case of image processing with AWS Lambda. In this scenario, we're going to have our mobile application users upload images and have those images be processed into various size thumbnails. Now, I think we all know that the internet loves cats. So in this case, we have an application dedicated to uploading pictures of cats. So the first thing that we need to do is enable our mobile application to have direct access to an Amazon service, such as the simple Amazon Simple Storage service. Now, by doing this, by uploading directly to an Amazon service, that enables us to bypass our backend API, and it can help reduce the load on that API. So the first thing that we're going to do is leverage the Amazon Cognito service, which in turn can interact with major login providers like Facebook and Twitter in order to have our user log in with those services. And by leveraging Amazon Cognito, we don't have to worry about the details of logging in with Facebook versus Twitter versus Google and so on. All we do is ask Amazon Cognito to handle that stuff for us. So the first step is that the user will log in with Facebook or Twitter. Amazon Cognito handles the details and returns temporary credentials, as we've talked about, back to our mobile application. Now again, those temporary credentials will only live for perhaps 15 minutes. So once they expire, we don't have to worry about rotating them. We don't have to worry about embedding credentials into our application. Once our application has those temporary credentials, we can then upload directly to an Amazon Simple Storage service bucket. From there, once the image lands in that bucket, an event will be fired that we can tie into a Lambda function, and the Lambda function can be invoked by that event. And details about that image will be delivered to the function. The function can then download the image from that S3 bucket, process it into various size thumbnails for different size devices, and then store the processed images in yet another Simple Storage service bucket. From there, this particular bucket would be used as what we call a distribution origin for the Amazon CloudFront service, Amazon CloudFront being our content delivery network. From there, those images will be served from edge locations out to the other millions of devices out there on the internet that are viewing these pictures of cats. So you can see here, by doing this, we don't have any infrastructure to maintain. We don't have EC2 instances that we need to launch and manage and create. We don't have really even an API that we have to worry about. In this particular example, we're leveraging services that are already inherently highly available and fault tolerant. So for application developers, leveraging services like this can really ease development and speed our time to market. And now as we go forward, we will see some of these use cases and demos that are introducing services that we haven't yet talked about. But the point here is to spur your imagination. I want you to start thinking of the possibilities of things that can be done within Amazon Web Services. I want you to start to see just how flexible all of these services are and how they can interact and play with each other to achieve just about anything you can imagine. So again, this is image processing with leveraging Amazon Simple Storage Service, Amazon CloudFront, and AWS Lambda. In this lesson, we will cover the wide variety of storage options, review demos of creating and using services like Amazon Simple Storage Service and Amazon Elastic Block Store. We'll review backups, archiving, and content delivery as well. Now let's take a look at an overview of all of the options we have for storage within Amazon Web Services. We have a number of different storage options in Amazon Web Services, and let's just start here on the left with what we call the Instant Store. The Instant Store refers to block storage that are essentially what we could say are built in to the EC2 instance. A number of different EC2 instance types come with different types of storage. It could be a small 30 gig volume, it could be several terabytes worth of volumes, and these are, now we say free, sort of highlighted here because the cost of that storage is included with the price of the machine, so you're not paying anything additional to the price of the machine for that storage. It just comes with it. Now, these drives within the Instant Store are considered ephemeral, meaning that when that EC2 instance terminates or stops, then whatever data is on that particular Instant Store will be gone. And that's because the Instant Store is backed by the volumes that are present on the physical host of that virtual machine. So when you stop a virtual machine or terminate a virtual machine, those stores will go away. Even if you were to stop a machine and start it again, it's most likely, probably almost even guaranteed, that that instance will come back on a different physical host. And so that underlying storage subsystem is no longer available. And so that's why we consider the Instant Store ephemeral. It's really important to know that, so that if you have applications that are writing to that, then if you lose that machine for whatever reason, if it fails, if you terminate it, if auto-scaling pulls that machine back in and gets rid of it, then that storage will go away. We do not have the ability to take snapshots, so there's no snapshot capabilities of the Instant Store. If you want to use that for its high IOPS capability, then backups will be something that you will have to do on your own. Now that brings us to another form of block storage, which is Amazon EBS, Elastic Block Storage Service. Now, the nice thing about this service is that these volumes, these disks, are independent from the machine itself. Typically what we would do is launch an EC2 instance, and then we would attach an EBS volume to that instance so that we can have a place to store our data. But because this device is independent from the machine, if we configure things properly, we could potentially lose this EC2 instance, but the data that's on this EBS volume will still be there because it's independent from the life of the EC2 instance. Now, it's important to know that as far as EBS goes, what we pay for is a storage, allocated storage per month. So if we allocate 1 terabyte for that volume, but we only use 1 meg, we're still paying for the 1 terabyte because that's how much we've allocated for the month. Or that's how much we've allocated for that drive. Now, with EBS volumes, we get a maximum of 16 terabytes per volume. And when we say that they're durable, it means that the EBS system inherently behind the scenes will replicate the data to numerous devices within a cluster in one availability zone. So EBS is to some degree already redundant, and it's resilient to the loss of a device within that cluster. EBS is not resilient to the loss of a data center. EBS volumes are created per availability zone. They don't span the entire region. So we do have the ability to create snapshots, and those snapshots are then stored over here in S3. So S3 is what we would consider object storage, and we're going to talk about the difference between those two here in just a little bit. So with S3, we can get storage, at least at the time of this video, storage was somewhere around 3 cents per gig per month. That's an incredibly low price for storage, and what we might describe Amazon Simple Storage Service as write once, read many. We might also describe S3 as storage for the internet. So we say that because S3 is a really great place to store things that need to be retrieved from millions of users out there across the internet. So we could put images that are meant for a website. We could put software patches, PDF documents, videos, all kinds of things can be stored in S3, and then we could send our users directly to S3, bypassing our own systems and reducing the load on our systems and just letting S3 handle the delivery of that content to our users. It's also important to know that all transfers use HTTP. That is the protocol for Amazon Simple Storage Service. Now, the last option that I want to talk about with AWS storage options is what's called the AWS Storage Gateway. This is a really interesting service in that ultimately what it is a virtual machine. This is published by Amazon Web Services, and it's designed to be run on premises, on an on-premises appliance using VMware or Hyper-V. And so you run this in your own local on-premises data center or co-location, what have you. And it exposes a device to which you can use as local storage. All of the data that is stored there will be also backed up, encrypted in S3 or Glacier. You can configure it to use either one of those services. If you use S3, we can use some other mechanisms that we'll talk about, like lifecycle rules, to get those files from S3 to Glacier in another way. The storage gateway comes in 3 possible configurations. One of them, that we call the gateway cached volume, means that the great majority of your data is stored directly in S3, but frequently accessed data is stored locally. That's the gateway cached volume. The gateway stored volume means that we're storing all of our data locally, but it takes regular point-in-time snapshots and uploads those snapshots to S3. And from there, if we wanted to, we could rebuild those snapshots as EBS volumes and attach those to virtual machines within EC2. The last one is what's called a virtual tape library, and that exposes an iSCSI interface, and it essentially looks just like tape, but that each virtual tape is stored directly in S3 or Glacier. So for those instances where you have a lot of data on premises and you have a lot of heavy workload, you're not ready to move all of that stuff to the cloud yet, or perhaps there are things that you never plan to migrate, you're going to leave it back on premises, but you want a good DR solution, then the AWS Storage Gateway is a really good option to consider. So those, at a high level, those are our storage options within Amazon Web Services. Now let's talk about the Amazon Simple Storage Service, otherwise known as S3. So S3, again, as we've mentioned before, is considered object storage. Now that's a bit different than block storage, and we're going to talk about that difference here in just a minute. But the Amazon S3 service, it's important to know that it's inherently highly available and fault tolerant. And we get that because the cluster already spans the entire region. S3 service makes use of every availability zone within that region. And so it's generally durable to the loss of 2 availability zones. So one of our very fundamental primary architectural questions we should always be asking ourselves when we design things and architect solutions for AWS is, what happens when this fails? Whatever that component may be. What happens when my storage fails? Well, if we're using S3, then we could say what happens when an availability zone becomes unavailable. Well, our data is already stored in another 2 or more availability zones. And so we have durability to the loss of an availability zone or to the loss of a data center. We get that baked in already with S3. There's nothing we need to do to make that happen. It's also important to know that within S3 there is no file system. Once we upload a file to S3, it's no longer really considered a file, it's considered an object. And there's just very simple flat hierarchy of buckets and objects within buckets, and that's it. It doesn't go any deeper than that. Now, if we notice up here, let's take a look at a URL through which we could download an object from S3. You will notice that we have a slash here, and that we can use slashes to form the semblance of a file-based structure, but ultimately there are no folders or files, there are objects. And so what we have here, we have a bucket called, in this example, my bucket, and we have an object called images/cat1.jpg. That is the key of that object, and it just so happens to include a slash. And so by doing that, we can form the semblance of a hierarchy, but ultimately it's still very flat. It's also important to note that in this example we're using HTTPS. There are times when you can get to S3 using just insecure HTTP, but it's recommended that anytime we're transmitting data to or from S3, we should be using HTTPS. It's also important to note that our bucket name needs to be globally unique among all of S3. So once you create a bucket, no one else in the world across every region will be able to use that name of their bucket, and that has to do with DNS. And you will see in some cases the name of the bucket is actually here as a part of the domain name. There is no limit to the size of the bucket or to the number of objects that are in that bucket. So you can store millions, billions or more objects within a bucket. You can grow into the petabytes and beyond, and Amazon does not impose any kind of limit to that bucket. Now, where we talked about with elastic block storage, you pay for allocated storage. With Amazon Simple Storage Service, we pay for what you actually use. So there's no need to pre-allocate anything. If you upload a meg, you pay for a meg. If you upload a terabyte or a petabyte, that's what you pay for. Now, we do have some limits on the size of individual objects. So individual objects can be up to 5 terabytes in size, but we should remember that we have an upload limit of 5 gigs per upload or per put request. And so if we have this limit on the upload size, but we have the ability to upload objects that are up to 5 terabytes, the way that we get these large files is through multi-part upload. And a lot of the Amazon tools, such as the command line interface and the SDK, will handle multi-part upload for us. Within Amazon Simple Storage Service, we also have the ability to leverage server-side encryption, and we do that by setting a flag per object at the time of upload. And Amazon Simple Storage Service will use AES, the Advanced Encryption Standard, 256-bit encryption. Amazon Web Services will also leverage a key per object. So every time you upload an object, each object gets its own key to be encrypted with, and that key is then encrypted by a master key, which is regularly rotated. So we have a very high degree of encryption available to us so that we can ensure that our data is encrypted both during transit and at rest using server-side encryption. Now let's take a look at object storage versus block storage and what it really means to store things on S3. So a good way to visualize this and understand the difference between object storage and block storage for those of us who might not be familiar is let's take the example of changing just one character in a 1 gigabyte file. You can see here that somewhere within this file we have some bits that represent that character. With object storage, if we wanted to change that one character, we would have to upload the entire 1 gigabyte file all over again, as opposed to block storage where we could just go in and change just the individual blocks that make up those bits that make up that character. Another difference is that with S3 being object storage, it uses HTTP or HTTPS for the transfer, which is a text-based transfer. It's going to be a lot slower than the more efficient protocols used by block storage, such as Instant Store and the Elastic Block Store service. Now, earlier we did talk about S3 being able to be mounted, but that's kind of an illusion. Ultimately, from a real systems level, it can't be mounted in the same way that block storage can be. We do have pieces of software that can create the illusion of S3 being mounted, but again, it's still using that HTTP for its transfer. So if you do that, if you use that software and, again, create that illusion of having mounted S3, you are not going to get anywhere near the performance of a block storage. So S3 is not at all the type of storage that we want to use for a database. We would want to use an EBS volume or an instant store volume, a block storage media for a database. S3 is perfect for database backups, but not for the disk to which the database would read and write its data. With block storage, we don't get random I/O. We either download the entire object or upload the entire object, and that's it. If you have applications that need random I/O, then block storage is going to be your best bet. So that is Amazon Simple Storage Service. Now let's take a look at a demo of creating buckets and objects within Amazon Simple Storage Service. You can see we're logged into the Amazon Web Services console. I'm going to go over here to Storage and Content Delivery and choose S3. You can see I have a number of buckets for various things that I've worked on, and I'm going to go ahead and create a bucket. And again, now this bucket name needs to be globally unique among all of S3 across every region that Amazon has. So I'm going to see if I can get away with this particular bucket name, AWS Live Lessons. And we're good. It let us create that. So now I have this bucket. You can see here from there I have properties of the bucket itself. I can control permissions such as a bucket policy, CORS configuration for dynamic websites. We could configure this bucket to host a static website. We could configure logging, events, versioning, lifecycle rules. We could do cross-region replication if we wanted to. If we wanted to have another bucket in a European region, we could configure this bucket so that anything that happened to it, it would replicate that data to another region. So I'm going to go into that bucket, and you'll see there's nothing in here yet. Now, one thing that I do want to draw your attention to is that while the UI gives us the option of creating a folder, that is really kind of an illusion. There is no file system within S3. Amazon Web Services has done some magic there with the UI on their side to create the semblance of folders and files. but ultimately it's still a very flat hierarchy. I'm going to go ahead and upload. From here, I could just drag and drop files if I wanted to, or I could click here and add files. I already have some files highlighted over here, so I'm going to grab this one, this mobile device picture, and I'm going to drag it here. We could see the details. I can upload that into the different storage classes if I wanted to, such as the infrequently accessed storage. I could use server-side encryption if I wanted to. For this particular image, I don't need that. I could set permissions. In this case, I could choose to make that particular object publicly readable, which I'm going to go ahead and do using object ACLs rather than a bucket policy. We could also set metadata if we wanted to. In this case, I'm going to let it figure out the content type automatically, but there are a number of different pieces of metadata that we could add, and it's always a good idea to go to the documentation and remind yourself and read up on the different kinds of things that we could set, such as expiration headers and so on. So I'm going to go ahead and start upload. You'll see, there we go, our object is uploaded, and you can see now we have an object in a bucket, and it's pretty simple. From here, I can click the object and see the properties of that. Here's a link that I can use to get to that object. I'm going to go ahead and click on that, and you'll see there we go, there's our object. And the only reason that I'm able to see that is because I set the ACL on that object to everyone being able to open and download. If I were to remove that and save it, now you'll see that this object is no longer publicly readable. I get an access denied on that. So that is our demo of creating buckets and uploading objects in Amazon Simple Storage Service. Now let's review bucket security with resource policies. We've talked about this before, resource-based policies. They are essentially the same as policies that we would apply to our IAM users and groups, but they are applied at the resource level. In this particular example, what we're going to look at is a policy that's applied to the Amazon Simple Storage Service bucket. We could also apply resource-based policies to other services like the Simple Queue service, DynamoDB, and others. One of the key differences that sets resource policies apart, aside from being applied at the resource level, is that we will specify what we call a principal, and that is who is allowed to perform these particular actions, or who is being denied these particular actions. So we could allow another account, so we could leverage that to give cross-account resource sharing. We could point the principal to a particular IAM user or group or role. We could give permissions to another Amazon service, or, as we're going to see in this following example, we could give permissions to anonymous users, anyone outside of Amazon, anyone in the world. So now let's take a look at an example. Here's an example policy that we would apply directly to an S3 bucket. So one of the first things that we need is the version. It's not semantic versioning, it's a date-based versioning, and we can find this particular value in the Amazon documentation. So here, again, we need to specify whether we are allowing or denying. In this case, we're going to allow anyone, that is anyone in the world, regardless of whether they have an Amazon account or not, to essentially download using the S3 get object action any object in this particular bucket. You'll notice that the /* means any object in the bucket, and we could have other types of permissions that would apply to the bucket itself. All right, so here's another example of a policy we might apply to a bucket that would grant cross-account access. So what we're doing here, if you notice, instead of specifying a star or a wildcard for the principal, which would, in the previous example, granted access to anyone and everyone all over the world, regardless of whether or not you had an account, this one here, we're saying the principal is going to be some member of AWS. In this case, we're pointing to an Amazon resource name that includes the account number of some other account that we want to share access with this bucket. And notice here, so that's going to be the account number, and then root is essentially, we're saying that that entire account or the root user of that account is allowed these kinds of permissions. And from there, that root user can then delegate these permissions to other members of that organization, to other IAM users. Now, this could be an account that we own, another one of our accounts like development versus production environment accounts. It could be a customer account or a vendor's account, some third party. It doesn't really matter. The point is that by specifying the principal as an IAM ARN using the account number and root is how we share a bucket across accounts. In this example, we are going to give that other account the ability to list the objects within the bucket. And so here, that particular action would actually apply to this resource, the bucket resource, and then the put object and get object actions would apply really to the objects within the bucket. So you'll see here that this is an important distinction between these two resources in the case of S3, being able to separate the bucket from objects in the bucket. And it's just a very minor difference in syntax between the /* there at the last one. So that is resource-based policies being applied to an S3 bucket in Amazon Web Services. So now let's take a look at another demo of creating a bucket policy to make a bucket publicly readable. So here we are back at the AWS console. I'm in the S3 service with all of my buckets listed. I'm going to click through to the bucket that we've created for these demos. You can see that we have our AWS Live Lessons bucket. We have our mobile device JPEG object that we've uploaded. And if I click on that and take a look at this link here, we'll see that it comes up as access denied. That's because by default, S3 is secure by default. You have to explicitly grant permission for someone to be able to read objects from that bucket. And so we could modify the permissions of that particular object using ACLs, but if we want to just make a blanket statement and say that everything in this particular bucket is publicly readable, then we would do that with a bucket policy. So I'm going to go in here to the bucket itself, scroll down here to the permissions of that bucket, and I'm going to add a bucket policy. Now I've already prepared one for this. I'm going to paste that in. And again, this is just like the policies we've seen. We have a version. We have our collection of statements. In this particular case, we only have one statement. The asterisk there, the wildcard, says anyone in the world can download an object from anywhere within this particular bucket. So I'm going to go ahead and save that. Now that it's saved, I'm going to make sure that I save this here again. Come over here, and when we refresh this, we should be able to see that image. And there we go. Now we're able to see that image. This is a really great example, too, of using S3 for things like static assets for websites. If you wanted to host all of your imagery, your product portfolio, CSS, JavaScript, fonts, whatever it is, S3 is a perfect place to store static assets. That way you can leverage the high availability and fault tolerance and performance of S3, have your users download these objects directly rather than having them get them from your web server. You can reduce the load on your backend services by just pushing that load off to S3. So that is a bucket policy being applied to a bucket in Amazon Simple Storage Service. Now let's talk about Amazon Glacier. With Glacier, we have access to what we call archival storage or cold storage. It's really great for things that we need to keep, like for regulatory reasons, like tax or health information, things that we just have to hold on to, but we don't necessarily need to get to very often at all. So we would call that archival storage. And you can see here that as of the time of this video, the price was less than 1 cent per gig per month. So it's an incredibly low price for long-term storage. Now, with comparing this to S3, with S3 being object storage, Glacier is very similar. It's just that it's geared towards storing, not for retrieving. Within S3, we had objects within buckets. Here in Glacier, we have archives within vaults. It's still that same very flat hierarchy. It doesn't go any deeper than that. With S3, we could describe that as write once, read many. One example is putting an image, a video, or a PDF file in S3 and then immediately allowing millions of people to read that. So that's one classic example of write once, read many. Whereas with Glacier, we would describe it as write once, read rarely, if at all. There are plenty of use cases where you put things into Glacier and then you never get them back out. It's just that you're putting them there because you have to, not necessarily because you need to read them. Though there are just as many use cases where you might put log files into Glacier and then a year or two later you might want to pull them out and do some sort of retrospective action on those files. With S3, we can download at will at any time. But with Glacier, because they're archived, we have to first do what we call a retrieval request and essentially inform the Glacier service that we want to pull things out. And from there, we will wait 3 to 5 hours for that file or that archive to become available to us so that we can download it. And the way that that works is that when we submit that retrieval request, behind the scenes, Glacier will copy that archive back to S3 and then send us some kind of a notification along with a link that we use to download that object. And of course, with Glacier, we pay for storage per month, and we also pay for retrievals. We're going to pay about 5 cents for every 1,000 pulls. So ways that we can get objects into Glacier would be, one, we can transition them from S3. We're going to talk about that here in just a minute. We could also upload things directly to Glacier if we wanted to. Now, let's take a look at what we call lifecycle rules. Lifecycle rules are a way to ultimately what we call manage the storage class of objects. When we put things into S3, typically they would go in as either the standard or the standard infrequently accessed storage class. That means that they are stored in S3. You can get a slightly lower price in S3 if you store them as infrequently accessed. That means that we're going to put things there. We might read them not as often as some objects, but more often than objects than we want in Glacier. And these lifecycle rules, we could do something like this, where let's say that we're putting log files into S3 and we prefixed all of our keys with logs / like this, and we have all of these different objects under that particular prefix. We could configure a lifecycle rule that says we want to archive these objects to the Glacier storage class, everything under that logs prefix, after 7 days. So a log file gets written to S3. 7 days later, it gets transitioned to Glacier, and then 2,600 days later, or about 7 years, it gets permanently deleted. So this is an automated way for us to put logs into S3, have them stay there for a week in case we want to do anything with them, and then automatically transition over to Glacier, thereby saving us a significant amount of money in the long run, and then automatically keeping them for 7 years before they're deleted. So that is Amazon Glacier. Let's take a look at another demo of adding lifecycle rules to an existing S3 bucket. Here we are in the console. We are in the S3 service, taking a look at the AWS Live Lessons bucket that we've created earlier. And here we want to add a lifecycle rule to that bucket so that we can automatically transition objects from S3 to Glacier after a period of time. Now, for these series of demos, we're just going to use this one bucket, and we can use prefixes to do that. So I'm going to leverage the magic of the UI here to create what appears to be a folder. I'm going to call this logs. Now you'll see here there's nothing in there yet, but perhaps later I might use an applications hosted in Amazon EC2 to write their log files to S3 and then keep them for some period of time before they are archived into Glacier. So I'm going to go over here to go back to the bucket itself. I'm going to go to Properties. I'm going to scroll down here to the Lifecycle section. And I'm going to add a rule. In this particular case, I don't want the entire bucket. I only want a prefix. So the prefix that I'm going to use is logs. So that means everything under the logs quote-unquote folder will be archived to Glacier. So I'm going to click Next. And you can see I can use the lifecycle to change the storage class to either the infrequent access storage or archive it to Glacier or permanently delete. So one common use case is for some kind of regulatory compliance, be it Sarbanes-Oxley or PCI or whatever it may be. We want to keep these for some period of time. So I'm going to archive to Glacier, let's say 7 days. So I'm going to keep them for a week in case I want to do some kind of computing with them, batch processing. And then I want to permanently delete them after about 7 years, so 2,600 days. So you can see here that if I were to upload something today, then 1 week from now, on November 10th, it would archive to Glacier, and then somewhere around 7 years from now, they would be deleted from Glacier. So I'm going to go ahead and hit Review. I'm going to call this one Archive Logs. And you can see here it says this will apply to objects with the prefix logs/ in the AWS Live Lessons bucket. It will archive to Glacier 7 days after the creation date and permanently delete 2,600 days after the creation date. So I'm going to go ahead and create and activate that rule. And there we go. We can see that we have a lifecycle rule in place for anything that goes into the logs folder. And that is how we add a lifecycle rule to an Amazon S3 bucket. Now let's talk about instance store volumes in Amazon EC2. Instance store volumes are volumes that essentially come with the EC2 instance. They're what we might consider built in to the EC2 instance, at least those instances that actually include them. Not all of them do. And so the nice thing about instance store volumes are, one, you're not paying anything extra. They're already included in the cost of the EC2 instance. We can get very high IOPS, upwards of 100,000 plus IOPS with these particular instance stores. But what we trade for that is the fact that they are ephemeral. It means that when we stop or terminate that machine, the data on that drive will be gone. Amazon does not give us the ability to perform snapshots on instance volumes. So there are plenty of customers that are using these instance volumes so that we can get that high degree of IOPS, but they are also leveraging some kind of other software, perhaps a custom-written application or a third-party application that helps back up that data to either S3 or the Elastic Block storage some other storage mechanism that has a longer lifespan and more durable. So again, it's really important to remember that while we do get this high degree of IOPS, the data on this drive is ephemeral. It could be gone. It will be gone when that machine is either stopped or terminated. Just as an example here, this is not a comprehensive list, but I wanted to give you an example of the types of volumes that we might expect to see with different types of machines. So one example here is the M3 Medium. The M3 Medium would come with one 4 gig SSD volume, whereas the M3 Extra Large would come with two 40 gig volumes. And yes, you could RAID them if you wanted to. You could put them into a logical volume manager. Some of the other instances you can see here, the D2 8 Extra Large comes with about 48 terabytes worth of volumes. That is 24 2 terabyte devices that are included with the hourly cost of that machine. And that is instant store volumes within Amazon EC2. So now let's talk about the Amazon Elastic Block Store. So we've talked about a number of different storage solutions, instant stores being one of them. There are plenty of times when our applications need a lot of random I/O, where object storage into simple storage service or Glacier just doesn't work. Instant store volumes are ephemeral. They don't have the durability that we need. So what we need is a volume that gives us a high degree or the ability to do random I/O, but also something that's a bit more durable, something that's not going to just delete itself if we lose our EC2 instance. So that is the Amazon Elastic Block Store. One of the really great things about this service is that the data or the device itself is independent from the instance. So EBS is built on a cluster of machines that are apart from our EC2 instance. They are connected over the network, but they are not to be confused with NAS. EBS is not network attached storage. Even though the protocol and connection is over the network, it's not the same thing as NAS. EBS volumes, we will pay for the storage that we provision. So if we say that we need a 1 terabyte volume, then because we allocate that for that volume, we're going to pay for that 1 terabyte, regardless of the amount of data that's actually being written to it. Now, it's important to understand that an EBS volume will exist in a single availability zone. So at the time we create that volume, we need to make sure that we create it in the same availability zone in which we will have our EC2 instance that we attach the volume to. And yes, we can encrypt these EBS volumes. We can either do so with an operating system level encryption, or we can leverage the EBS built-in encryption mechanism. Now, I like to think of these very much like we think of like a USB external hard drive. A USB hard drive I can plug into my laptop, just like we have this EBS volume attached to an EC2 instance here. We have the ability to detach it and reattach it to another machine. I could detach it for that one and reattach it back to the original one. Just like you can with a USB hard drive, you can unplug it from one laptop and go and plug it into another one. But we can only have one EBS volume attached to one instance at a time. We can have multiple EBS volumes attached to one instance, but one volume can only be attached to one instance at a time. And yes, we can RAID them as well if we wanted to. From my experience, I've seen RAID not necessarily give you any better performance, especially RAID 5 and RAID 1. It's not going to necessarily increase performance. You're not necessarily getting the redundancy because EBS is already inherently redundant to a degree. It's resilient to the loss of a device. So you already have the redundancy built in. In some cases, I have seen some better performance using RAID 0 across multiple EBS volumes. And yes, you can add them to a logical volume manager. As far as your operating system is concerned, it's just a volume like anything else. It just so happens that EBS is connected over the network. So that is Amazon Elastic Block Store. Now let's review EBS volume types and performance. EBS volumes come in a number of different types of volumes. We do have access to SSDs, which come in a couple of different flavors, and then of course traditional disks, which come in their particular flavors. So under SSD, we have volumes that are just what we call general purpose, good for a number of types of applications. We have provisioned IOPS as well that's going to give us a guaranteed level of throughput, or IOPS, which is really good for databases where you need to guarantee a certain level of performance. So you can see here that the general purpose SSD is going to give us somewhere around 10,000 max IOPS, but a baseline of 3 IOPS per gig. So a 100 gig volume would operate at about 300 IOPS. Whereas with provisioned IOPS, we actually specify the exact amount of IOPS that we want to be guaranteed. So in the case of high performance computing or databases, I've regularly see databases that need a consistent 1,000 to 2,000 or more IOPS all the time. And so that would be a good opportunity to use provisioned IOPS so that we can guarantee that we get the level of performance that we need. Now you can see here with provisioned IOPS, we can go up to a maximum of 20,000 IOPS per volume, but we do have a slightly higher minimum. We have a 4 gig minimum as opposed to a 1 gig minimum, but we have the same upper limit of 16 terabytes per volume. You can see here that the SSD volumes, both general purpose and provisioned IOPS, are really geared towards the IOPS. They're geared towards random I/O, and we get a fair amount of throughput, but if you have applications that really need a high degree of throughput, where you're not really worried about random I/O, you're worried about just getting data to the device sequentially or reading data from the device, then perhaps the traditional disk would be more appropriate. In that scenario, we have one that is throughput optimized that can give us upwards of 500 megs per second, but you'll notice that we don't get near the amount of IOPS as we do with the SSDs. We get about 500 max IOPS in that case. And again, we have upper limits, very similar to the SSDs, we have upper limits of 16 terabytes. So those are the options that we have within EBS, either SSD, general purpose, or provisioned IOPS, or the traditional disk, throughput optimized, or cold storage. Now let's review another demo of creating an EBS volume within Amazon EC2. Here we are back in the console. From the console dashboard, I'm going to click into EC2. I'm going to come down here to Elastic Block Store Volumes, and you'll see that we have one, but this one is the root volume. You can see that it's in use. It's considered to be in use. This is the root volume of our Windows instance that's still running. But I'm going to create a new one, perhaps a new one that I want to attach to an instance and use as a data volume apart from the root volume. So I'm going to click Create. From here, I can choose whether or not I want general purpose SSD, provisioned IOPS, magnetic, throughput optimized, or cold storage. So for this particular case, I'm just going to choose a general purpose. It's just going to be a basic data volume. I'm going to say leave it at 100 gigs. I'm going to make sure that this one is in 2B because that's where we put our Windows instance. So I need to make sure that this volume is in the same availability zone as the instance to which I want to attach it. Now I have the option to encrypt the volume if I wanted to. For this particular demo, I'm not going to worry about that. I'm going to go ahead and click Create. And then you'll see that the volume is in a creating state, so it takes it a few minutes to make that volume available. It's allocating the storage behind the scenes. So here, I might call this one data volume, just to give it a name and keep my environment organized. And there we go. Now you can see that the state of that volume is available. That means it so far is not attached to any particular instance. So we could then use it however we want. We can attach it to whatever instance we want as long as the instance is in the same availability zone. So I'll go ahead and create one more while we're here and make this one a provisioned IOPS. And so I'm going to say, you know what, I want a 100 gig volume, and where the general purpose would have a baseline of about 300 IOPS, here I could say, you know what, I need more than that. I need 1,000 IOPS, and I'm also going to put this one in 2B. So this is how we would go about creating a provisioned IOPS volume, by specifying the size and the degree of IOPS that we need. I'm going to go ahead and hit create, and again, I'm going to call this one data volume high IOPS. And there we go. You can see that our general purpose has a baseline of about 300 with the ability to burst up to 3,000. But our provisioned IOPS will guarantee us a consistent performance level of 1,000 IOPS. So that is creating EBS volumes in Amazon EC2. All right, so now let's run through a demo of mounting an EBS volume to an existing Linux EC2 instance. From the Amazon Web Services console, I'm going to go back to EC2. I'm going to go to my volumes. So we're going to choose this particular volume. Doesn't really matter which one, but for the sake of this demo, we're going to choose the provisioned IOPS volume. I'm going to click Attach Volume. I'm going to choose the Linux server, and I'm going to mount it at dev SDF. And of course, we could go from SDF through dev SDP. And I'm going to go ahead and hit Attach. And we'll see that now the volume is labeled as in use, but down here, the attachment says that it's currently attaching. So we're waiting for it to become fully attached. We can hit the refresh button, and now we see that the volume is attached. So I'm going to open an SSH shell into that instance. And from here, I'm going to list the block devices that I have. You can see here that here is our root volume with our partition on slash, and then XVDF is how it got renamed. We actually mounted it or attached it within the console as SDF, but the operating system renamed it to XVDF, and that's okay. So you can see we have the 100 gig volume, and it's just a disk. We don't have a partition on that yet. So from here, I'm going to format this as ext4, and I'm going to use /dev/xvdf. And there we go. Just like that, super easy. We were able to format that with ext4. And now I want to create a mount point. I'm going to create a folder called, let me make sure that we have that /mnt/data. So that's going to be our mount point. Now I want to mount the volume to that mount point. So I'm going to say sudo mount /dev/xvdf will be mounted to /mount/data. And now if I were to do a df, we can see now that /mount/data is mounted to the dev xvdf device, and we have just about 100 gigs available. So that is mounting an EBS volume to a Linux instance. Now let's review a demo of mounting an EBS volume to a Windows instance. From the EC2 dashboard in the AWS console, I'm going to go down here to our volumes. You can see here a couple of volumes that we created earlier. I'm going to choose one of these, the data volume, and the first thing that we need to do is attach it to the instance. So I'm going to click Attach Volume. I'm going to click here and it'll automatically give us the ability to choose which instances. Right now we only have the Windows server running. I'm going to click that one. I'm going to leave this as XVDF. And of course we could go through XVDP if we wanted to. So I'm just going to leave that as it is. And I'm going to click Attach. And you can see that now our volume goes from an available state to in use. So that means that it's attached. And you can see here that it shows the attachment information as being attached to our Windows server, and it's still in the attaching state. So while that attaches, I'm going to go ahead and open another RDP session into our Windows EC2 instance. So now that we're here, we have an RDP session open to our Windows server. I'm going to go into the server manager. And I'm going to go to File and Storage Devices, Disks. And you can see that we have our 100 gig volume that we just attached. I'm going to right click on that one and say Bring Online. I'm going to say yes, I am sure that I want to do that. Once it's online, I'm going to initialize that. And yes, I know that it's going to erase the data, but there's nothing on there. It's a brand new device. So yes. And there we go. Now that we have that device available, we can do with it as we need to. We can format it, we can leverage it for storage, whatever. So that is mounting an EBS volume to a Windows instance. Now let's talk about EBS snapshots. EBS snapshots are a tool that we can use to increase the durability of the data stored on our EBS volumes. Now, EBS volumes are, in a number of ways, a really great tool to use within AWS just because they're independent from the life of the EC2 instance. We have a lot of control over the performance of that volume, but they do exist in a single availability zone. And while they are durable, they have some degree of resilience. They're resilient to the loss of a device within the cluster. They are not durable to the loss of an availability zone. So going back to our fundamental architectural question, what happens when this device fails? What happens when we lose an availability zone? Even though it might be rare, it could still happen. We have to plan for it. What happens when we lose an availability zone? Then we should have a good answer to that. And the answer is, well, we have snapshots of that volume that are stored in S3, which is inherently highly available. S3 is durable to the loss of up to 2 AZs, so that means our data is still there, and we can recreate that volume from that snapshot in another availability zone. So when we take a snapshot, let's say we take a snapshot of this volume, that snapshot will be stored over here in S3. Now, I like to think of that being stored in some kind of like what I call an admin zone, and I say that because we don't have direct access to the raw storage of the snapshot, but we do know it's stored in S3. What we have access to in the Amazon console, we will see snapshots as a resource that we have access to. We just can't get to the underlying raw storage in S3. AWS makes it really easy with the command line tools, with the SDKs, even the console, to copy that snapshot to another region. So for disaster recovery purposes, we might want to create snapshots here, and then perhaps our business policy or some type of regulatory policy says that we need geographical diversity in our data. we can use this copy command to copy that snapshot to another region, and perhaps we have our initial data stored on the West Coast, and we copy that to a region on the East Coast, and now we have several thousand miles between our copies of data, and that gives us our geographical diversity. We can also share snapshots between accounts. If we're doing something with data in the production account and we want to get that back over to some kind of development or test environment in another account, we can do that as well. We can share that snapshot to another account. The first time we take a snapshot of an EBS volume, we are going to take all of the data that's on that volume, and that will become our snapshot. From there on, subsequent snapshots will be incremental. That is, only new data or data that has changed. You can see here that these blocks have changed. And then, of course, we have another couple of blocks that are new data. So only those blocks that have changed or become, new data will be a part of that subsequent snapshot. So again, EBS snapshots are the way to increase the durability of your data, to get geographical diversity of your data, and a way to recreate your volumes in the case that they're lost or accidentally deleted or whatever. So that's EBS snapshots within Amazon Web Services. Now let's review a demo of creating a snapshot within Amazon EBS. From the AWS console dashboard, I'm going to go back to EC2. I'm going to go back to my list of volumes. You can see we have several data volumes here. So from this volume, it could be a 100 gig volume, but perhaps we only have 10 gigs of storage on it. Doesn't really matter. One thing that we should keep in mind is that if we are making regular snapshots of our volumes for the sake of durability, for the sake of backing up that data, we should take these snapshots with no more than 20 gigs of dirty data, meaning that if we wait too long and we have enough data has changed so that the snapshot causes 20 gigs of data to be backed up, then we can see a performance hit while the snapshot is in place. So creating a snapshot is really easy. We just highlight the volume that we want to snapshot, go to Actions, and create snapshot. From here, I might put the date, or I'm just going to call this one AWS Live Lessons Backup. And we also need a description. A lot of times I just use the name over again. And then once we have the name and the description, we can hit Create, and the snapshot creation has started. So that means that this volume is in the process of creating a snapshot. So if we go over here to the snapshots, we can see that this one has already completed. That's because we don't really have a whole lot of data on there. Didn't take very long. But if we had this volume with upwards of 20 gigs or more worth of data, then it would have taken a bit longer for that snapshot to complete. So this is just one way to create a snapshot here through the console. The other ways would be to leverage the command line tools or the Amazon SDK and do it programmatically. So it's a very common practice to write scripts that leverage those tools that automatically do these backups at a prescribed period of time. So now that we have our snapshot, from here we could do a number of things. We could copy that snapshot to another region if we wanted to. You can see here it's in Ohio, but we might want to copy that to some other region, any other region around the globe, and give some geographical diversity to our data if we wanted to. We could also create a volume. You can see here we could recreate another EBS volume from that snapshot and put that volume in another availability zone or the same availability zone. That's up to us, depending on whatever it is that we're trying to achieve. So that is creating snapshots from existing EBS volumes in Amazon EC2. Now let's review a use case of video transcoding and archival in Amazon Web Services. In this particular use case, what we're looking at is an Amazon EC2 instance launched as a G2.2 extra large, which has access to some very powerful GPUs. And we're going to use those to render a 3D animation to the disk. And because we have a lot of information going to the disk sequentially, we went with a throughput optimized hard drive instead of an SSD provisioned IOPS or general purpose. Now, once this animation finishes rendering, what we want to do is take that high resolution master and we're going to upload that to S3. S3 would then be configured to lifecycle those masters off to Glacier after 7 days. So sometime within that first week, we might do something with the master. And then after that, we want to keep it for a long period of time, but we just want to lower our cost of storage, and so we're going to leverage Glacier to do that. Now, once this object, the high resolution master, has been uploaded to S3, we're going to leverage S3 events to trigger a Lambda function. One Lambda function will take the metadata of that video and it will store that metadata in an Amazon DynamoDB table so that we can reference that later. And we might correlate that metadata, one, back to the file that's stored in S3, and we might also correlate that metadata to the objects stored in Glacier as well. At the same time, that same event will also trigger an additional Lambda function concurrently. You can see here we're leveraging the S3 object created post event to invoke these Lambda functions. The second Lambda function will be used to trigger the Elastic Transcoder. The Amazon Elastic Transcoder is a service that we can use to transcode this video into a number of different formats. Now, again, this is the high resolution master, but we want to get this video out there to people to view at a number of different formats, different screen sizes, different platforms, and so on. So we're triggering the Elastic Transcoder, which will pull that video from S3. It will transcode it into various sizes. It will output all of those, perhaps a half a dozen different videos, to S3, to another bucket. We will use that bucket as what we call the origin for a CloudFront distribution, and then we can use CloudFront so that these final output videos are served to other users from edge locations. Some of these things we perhaps haven't talked about yet, and again, as far as these use cases and demos go, I want to spur your imagination. I want to get you thinking about the possibilities. I want you thinking about ways that you can leverage these various services, perhaps in similar ways, to solve the problems that you're facing in your particular business. So that is just one example of the virtually limitless possibilities that we have to put these services together within Amazon Web Services to solve technical challenges, and that is video transcoding and archival within using the various storage options we have available.